Yeah. Yep. Although, first of all, All right, I think we'll get started. So clear my throat. I guess I should do that first. So thanks for joining us for the last day of the conference. Today, you probably see on the schedule, it's an abbreviated day. So we'll wrap up now at 3. We'll give a couple reminders about this, but so we did have a small schedule change. There's one, like the last talk on the printed schedule is now going to be moved to the first talk of the session following the keynote. So we will actually have a normal 30-minute break after this keynote and restart here at 10:20. So just be aware of that, even though the printed schedule says, I think, 10:40. Just a couple other kind of housekeeping reminders. First off, thanks for everybody who participated yesterday in the 2 networking events. So from what I've heard, the in-person one here had a lot of good conversations. I moderated the virtual one, and we had a few folks in there, and we sort of had a nice free-form conversation about all sorts of different topics and a little discussion about what AI is going to do to our jobs, which was always fun, I guess. But yeah, I hope that was worthwhile, and again, appreciate you for bringing your energy to it. Also, it was nice to see so many folks out last night at Rosetta Hall. So yeah, thanks for those who came and spent the evening with us. Just wanted to give one final reminder about the Jupyter Notebook proceedings. So those are intended to be sort of due at the end of the week. If you have any questions about that, please do let us know. So we're going to have one more office hours. And again, that's just kind of a space at the end of today to come and ask questions, get help. If you're still on the fence, there's still time. So we'd be happy to talk to you if you think you might be interested in submitting. That's going to now be from 2 to 3 p.m. today, not from 2:20 to 3:20. So we will wrap up the day as a whole at 3 p.m. If you're going to spend any extra time in Boulder, hope you enjoy it. and go skiing or whatever sounds fun. Another thing, so we'll be sending out an email. I think this is all going to go in an email that's probably going out now. But we're going to send out an email sometime soon with a post-conference survey. We'll try to keep it short, but that's always useful for us to know what you enjoyed and what you think could be improved or what you'd like to see in the future. So I do hope you get a chance to fill that out. Also, we have, I want to say 14 people on the ISS committee this year, and really appreciated all their contributions. If you think you might be interested in helping us out plan next year's conference, we'd love to have your participation. And that's not limited to UCAR and NCAR staff. So think about it and just send us an email if that is something that's of interest. I think I might put a question along those lines in the post-conference survey as well. So, again, you got time to think about it. I don't think we'll actually kick off that process until, I don't know, the end of the summer or beginning of the fall. So, and hopefully it's not too time intensive, but if any of the committee members want to shake their head and say it is, that's fine. And then finally, I did want to touch very quickly on like everything that's going on outside of this conference, which is kind of crazy. So obviously there's a lot that could be said about it, and we haven't wanted to do that because we wanted to let everybody here sort of present their work and bring their energy and not have to think about like outside concerns. But that's definitely really hard to do right now. Like it's hard not to like bring up the news on your phone. So I think, well, I believe that conferences like this and others like it show the kind of the positive impact that collaboration has and sharing of ideas has, and it's super important and it's super vibrant and it's fun. So this year we've had people join from many different institutions, many different backgrounds. We've had a lot of international collaboration, which is awesome. So we're happy to have you. And I've had a ton of really cool conversations with a bunch of different people this week, and it's been great. And I say that as somebody who's like a pretty hardcore introvert sometimes, and my social battery like wears out. But at the end of these conferences, I'm always excited to do work and think about cool new things. So that's super valuable, I think. Despite all of like the headwinds that we've encountered, we've had more people show up at this year's conference than last year's conference, which I think is awesome. We weren't sure how successful we were going to be this year, but I think it's turned out great. So that's like kind of a credit to everybody in this room and virtually. I'm guessing that some people here may have had more pushback in attending than they would have had normally, but you came anyway, so really appreciate that. And, I guess kind of summing up my thoughts, like, regardless of what anybody says, the work that we do matters, right? And we all matter. So, I think everybody knows that, but, just keep it in mind. So again, thanks for coming. I hope you enjoy the final day of the conference, and I hope we get to see everybody next year. So with that said, I'm going to hand it over to Caitlin, and she's going to introduce our keynote speaker for the day and then sort of moderate that session. So thanks again.
We get a quick round of applause for Brian for chairing the conference. I don't know if it's obvious from everyone else's perspective, but he put in an incredible amount of effort into both kind of revitalizing the organization as a whole and organizing this conference this year and I believe in prior years. I'm not sure how many offhand, but yeah, maybe another quick round of applause. And with that, I'm excited to introduce our invited keynote speaker today. Ligia Bernadet is a meteorologist with a PhD in atmospheric sciences from Colorado State University. She's the chief of the Earth Prediction Advancement Division within the NOAA Global Systems Laboratory in Boulder, Colorado, a member of the Unified Forecast System, or UFS, Steering Committee, and co-leads the Community Earth System Model CSM Software Engineering Working Group. Her experience in code management and user support for community models has given her an appreciation for the importance of software engineering best practices. And we're really excited to have her presenting here today. So her talk will be entitled Earth System Model Development Activities at the NOAA GSL, a Software Engineering Perspective. And with that, I'll turn it over.
All right. Well, thank you so much. Can you hear me okay? If not,
we can, yeah.
Okay, great. When I share my screen, I don't see you guys. So if you need to talk to me, please just interrupt. Thank you for inviting me. This is really exciting. I tried to get there in person, but there was an enormous traffic jam near my house in Longmont leading to the diagonal. So after a while, I had to turn around and come back home. So that's where I am speaking to you. And I really appreciate Brian talking a little bit about the big picture here of the entire situation. I'm so happy that invited speakers don't have to pay to register, because otherwise I could not participate in this conference, because we cannot, federal employees at this time cannot spend any money to attend conferences. So this is really a treat to be here with you today. So as the introduction already said, I am a meteorologist. I am not a trained software engineering. But right now, I'm leading a group in model development and evaluation, which is called the Earth Prediction Advancement Division. And that's part of one of the NOAA research laboratories called Global Systems Laboratory, and it's located here in Boulder, Colorado. And these aspects of model development do give me an appreciation for software engineering, something I have cultivated over the years. So I'm going to try to speak to you from this perspective. So today, I will give a brief introduction to the Global Systems Laboratory and talk about some of the modeling systems that we work with. Some of them are WRF-based, and they have acronyms like the RAP and the HER. I'll talk to you about the UFS, the Unified Forecast System that we are using for prediction from short-range weather to seasonal, so many months. Our foray now new with the MPAS model and also higher resolution applications with additional models. And to do all that, we face a number of software engineering challenges and seeking solutions. So I'm going to not be going too much in depth into any of the topics, but it's going to be more of a broader presentation. But some of the aspects I will touch on are the separation of concerns and modularity in terms of the software we develop and how that benefits us. Aspects of distributed development and distributed computing, how we've been handling that. Big emphasis for us, which is in community engagement and gathering community contributions. And finally, new work that we are doing in artificial intelligence, going beyond the physical models into data-driven solutions. So the Global Systems Laboratory has a vision, which is written there, to develop systems that deliver solutions to make forecasts better. So just to unpack that a little bit, the goal is to make forecasts better. And, by that we mean like weather forecasts or Earth system modeling forecasts. But we are NOAA Research. We are not the Weather Service or the Ocean Services. So we don't make ultimate forecasts. We just provide models or other tools that help forecasters and the Weather Service deliver what they need. And to do that, GSL has a number of strategic goals. So in this presentation, we'll focus on goal number 2, which is to develop state-of-the-art Earth system prediction capabilities. So I borrowed this diagram. I'm not sure it's the best of diagrams, but I wanted to give some idea of the different aspects of Earth system model development that we work with. So on the y-axis here we have atmosphere, the interface between atmosphere and the ocean. And GSL works mostly with the atmosphere, but we do have some work in ocean modeling, and especially on the ocean and sea ice and their interface with the atmosphere. We also do a lot of work in land surface modeling and how it interfaces with the atmosphere. We work mostly in the physical realm, so we do some chemical and biological research, but very little. And within the physical realm of our system modeling, we work on a different number of scales, from what we call high resolution nests, which are 1 kilometer and sub 1 kilometer, to regional or limited area modeling on the order of 3 kilometers, to global forecast systems ranging on the order of 13 kilometers for medium range weather, all the way to much coarser timescales for seasonal forecasts. And the seasonal forecasts go to, here's listed 100 days, but we have forecasts going out to 9 months as well. And to do all that, we work in data simulation, in the development of physical parameterizations. We do quite a bit of work in atmospheric composition. We use observations, of course, both for data simulation and for the verification of the models. And then more recently, within the last 2-3 years, we've also been engaging in artificial intelligence and machine learning. So here I'm starting to describe one of the models a couple of the models that we developed at GSL, called the RAP and the HER, which are WRF-based models. The RAP is the rapid update cycle, and the HER is the high resolution rapid refresh. And this slide here on the left side, we have reality, so observed composite reflectivity for a certain forecast. And one of our main applications is aviation. So we are very interested in doing short-term forecasts of where thunderstorm is going to be, so that airlines can figure out the best routes, but also improve their fuel usage and be more safe. And this is a kind of throwback. So going back to 2012, 10 plus years ago, all we had was the REP model configuration, which was 13 kilometer grid spacing. In 2014, we had the first implementation of the HER model, now going to 3 kilometers grid spacing. And it's obvious that, that bought us a lot better forecasts and a lot more detailed representation of the storms to guide our aviation. Since then, since that implementation in 2012, 2014, we've had a number of implementations of the HER model at 3 kilometers. So in 2016, HER version 2, in 2018, HER version 3. Actually, it's not listed here, but in 2020, we had HER version 4. All those were actually capped at 3 kilometer grid spacing. So we're not necessarily subscribing to going to more resolution is always better. And we've looked at improvements in the model via data simulation and physics. So here we see this set of supercells in Oklahoma, and how, earlier model configurations were not representing those, but more recent ones have a better representation of this particular case here. A big thing for us is also obtaining probabilistic information, and that's part of our mission in delivering solutions. So a lot of the decision making is based on knowing the uncertainty of the forecast, of the range of scenarios that may take place, or the range of times in which a certain snowstorm or phenomenon may hit. So we've been working not only with the deterministic HER model, which is represented here in these various curves in yellow, but also with the HREF ensemble system at 3 kilometers, which provides us, here we have composite reflectivity, here we have a 1 hour precipitation or 24-hour accumulated precipitation. This is just for a single forecast. So the ensemble prediction is really important, but of course it stresses the computational resources and poses more need for thought and software engineering. And we don't work just with meteorology. So a good part of our portfolio is on fire and atmospheric composition. So this is a forecast using the HER smoke model, in which we have tracers for smoke a newer version of our models, we're also predicting dust as well. And the key thing is to produce actionable information with a minimum number of constituents or tracers in the model. So as you know, each additional tracer costs a substantial time of computational resources. And we're trying to create a very simple model, but that can be very informative to those doing decision making. So this is the HER smoke, and we are now working in a new version that's already running in real time, in which we're adding also pollen as a variable of interest to the population. So as I mentioned before, these applications, the RAP and the HER, use the WRF model. And so leveraging community modeling is a major and integral part of what we do. We have been involved in the WRF community, both as like users of the model, as well as major contributors, especially in the area of physical parameterizations for a number of years. And so this is the image I just got here from the M-Cubed website, and they themselves are displaying their gradual transition to the MPAS model, and this is something that we are also working toward, and I'll talk a little bit more about our transition to MPAS. So now, switching gears from the WRF, MPAS, NCAR realm of models, I wanted to talk to you a little bit about other models that we're using in the NOAA production suite. And NOAA production suite refers to the National Weather Service and their NCEP Center, the National Center for Environmental Prediction, which executes, so runs in operations, a number of forecast models to provide the material for human forecasters and other decision makers. And we see here on the left side of this diagram that this is from 2022, but it's actually not so different right at this time, that there's a number of forecast systems, with the RAP and HER being just one of them in this big list. And the issue with this very long list of models here is that it is very difficult to maintain and develop, because these models use different dynamical cores, different physics, different workflows, but they also have different like code bases. So even similar models are not referring, say, to the same physics repository, and so there is an enormous duplication and overhead of developing such a complex system. So there were a number of reviews in which external community members came to NOAA and provided input on how this could be improved. And the idea is to reduce the number of these applications by consolidating some of them, and having just a smaller set of applications provide all the forecasts and products that downstream users need. So this brought the impetus of developing the unified forecast system. And from this, maybe I'll go to this slide here first, provided the impetus for the development of the unified forecast system, which could be defined as a common infrastructure which is modular and can be assembled as building blocks into a number of applications to meet the users and forecast needs. The unified forecast system is meant to stimulate research and be used in academics. So this is not the NOAA UFS. This is the UFS for NOAA and everybody else as well. We want the community not only to do research and use the model, but also have a way to conduct development that's of interest to them. And we want to facilitate the transition of this development into operations. For that, we stimulate development to be done in the same code base and modeling system as it's going to be used in operations. So in addition to supporting this research and development, we want to be producing, of course, the best forecasts possible, and overall streamline this forecast production suite. So just I'll go back to the slide I had before. So from these building blocks of the UFS, we intend to create this application. So we have medium range weather out to a couple weeks, subseasonal to seasonal, going out to 9 months to approximately 9 months. We have the hurricane application, which is based on, tuned, let's say, for a specific weather phenomenon. Short range weather, those are going to be the next generation after the REP and HER and the HREF ensemble. We have applications in space weather, coastal applications for storm surge and coastal flooding, and finally, air quality. Okay, so let me go back where I was. So as I mentioned before, what makes the UFS is its infrastructure and its code management and the fact that we assemble those building blocks, but all the applications go forward using a single code base. So having this modular infrastructure is a key part. Some of the community codes that we are using are the JEDI for data simulation, the UFS weather model, which is a coupled modeling system. So of course it has an atmospheric component. Today, it only works with a single dynamical core, which is the FV3 developed at the NOAA GFDL laboratory, but we're working to bring in the AMPAS dynamical core as an alternate. And for the physics parameterizations, we use the CCPP or Common Community Physics Package. Then we have other components such as WaveWatch. Ocean is the MOM6, CI is SI6. And for atmospheric composition, we're using both GoCart, which is from NASA, and CMAC from the EPA. Then to connect all that together, we use the ESMF or system modeling framework. It works both in intercomponent coupler, that meaning coupling between the atmosphere and the waves and the ocean, sea ice, etc. But it also is used to drive the model forward. It provides data models or like canned data cases to substitute for active components, and also controls our asynchronous IO or write grid component. For post-processing the forecast, we use UPP, that's the Unified Post Processor. And finally, for forecast verification, we use the MAT Plus or Model Evaluation Tools, developed in great part by NCAR under the auspices of the DTC Developmental Testbed Center. So I just wanted to spend a few, I think I have 3 slides or so on the Common Community Physics package. And the reason that I'm narrowing over this particular component over all others is because I am personally more involved with this. It is developed under the auspices of the DTC, but a lot of the development takes place within NOAA GSL. So the CCPP is a library of physical parameterizations with associated framework for use in weather models. So in this figure here on the lower right, you can see in the bottom, the CCPP physics library in this gray box. And the library has a number of physical parameterizations for different types of phenomenon, like surface layer parameterization, boundary layer, convection, microphysics, etc. And this is interoperable library in the sense that it can be connected to a number of atmospheric drivers, so it is host agnostic. The way by which this connection is made is through the CCPP framework, which is the software that connects the library to the driver. And this connection is done to this, what we call the metadata tables or variables, in the sense that the physics communicates the information about the variables that it needs to execute each of these parameterizations. The host model communicates information about which variables it has, and the exchange is done through the creation of auto-generated physics caps that are built in the model executable to exchange information in runtime. So this facilitates our research and development because those interfaces are really clear, and we can use this both in the UFS where it is already operational, but it can be used also in other models. It is on track for use by the US Navy Neptune model, and it's being adopted by selected NCAR models such as CAM-CIMA for future use in CESM. So I talked a little bit about those, the way in which we transfer variables between the physics and the host models, and we use standard names of the variables as the main type of metadata that's used to describe variables. And this, I'm just highlighting here that we have a dictionary of the standard names used by the CCPP, which contains the definitions of all the variables as well as rules to create new names. And this dictionary is now being used also by JEDI Data Simulation and other groups, highlighting the importance of this modularity and clear interfaces efforts. CCPP has a number of capabilities. It allows things such as choosing the suite, the physics suite that you want to have the model run at runtime. It allows different ordering of the physical parameterizations. It allows subcycling of the parameterization, so calling some of the parameterizations at higher frequency than others, grouping parameterizations together so that you can call other parts of the model in between, for example, calling aspects of the die-core or coupling to other model components in between the parameterizations. And it also allows automatic unit conversion. So for example, if a certain parameterizations provide a variable, say in meters, and the dynamical core has that variable in micrometers, those conversions can happen behind the scenes and not impose more work to the developers and implementers. The CCPP also, due to its interoperability, also opens doors for simplified modeling and what we call hierarchical development. So when you're developing physics, it can be helpful to execute it not only in the context of the fully three-dimension, fully coupled weather model, but also use, say, a single column model or other or simplified construct. So we connect the CCPP physics to our own single column model, which can be initialized and forced for a number of case studies to see how the physics performs in specific meteorological and geographical locations. And the single column model can also be forced by UFS runs if you want to study certain biases or characteristics of the UFS runs. In the future, it can be extended to also be forced by runs from other, interested host models. Okay, so switching gears a little bit, going back to that bigger Unified Forecast System or UFS, as I said, we have been running the WRF-based rapid HER models up until, not up until, they are operational today, but there is an impetus to start using the UFS, the Unified Forecast System. And so this convective allowing 3-kilometer application was developed, and it's called the Rapid Refresh Forecast System, or RRFS version 1, which was developed to subsume some of the existing operational models to simplify the NCAR production suite. And this model is now undergoing tests at the National Weather Service for a potential operational implementation in the next calendar year. While doing that, while testing this RRFS model, specifically in the springtime, a number of challenges were noticed, and they are described here in this white paper by Jacob Carley and others. And the problems have to do with excessive number of storms. So in this plot here, we're comparing on the right observations, on the left, the HER version 4, and in the center is the new RFS model. And so this excessive number of storms that were seen in the model led to a large frequency bias. So here we have frequency bias of precipitation as a function of amount of precipitation, so going all the way up to 2 inches or half an inch, 1 inch, 2-inch accumulations. And a number of mitigation efforts were brought in to try to reduce this problem. And the problem did get better, but in the end, after lots of investigations, it was determined that there were shortcomings of the FE3 dynamical core for the representation of this very strong and severe convection springtime in the central United States. And because that is such a critical part of the forecast that need to be delivered by this model, it was decided to start pursuing and doing research and development on the use of the MPAS dynamical core for future UFS implementations, in particular for the 3-kilometer resolution. So since then, we have been doing a lot of work with MPAS. So in GSL, we are now running MPAS in global time, in real time for a number of applications. We're running it in global, CONAS, also hurricane applications. Currently, we're only running real time with cold starts, but pretty soon we'll be starting doing runs using the JEDI for data simulation. And just to summarize here, we're doing daily runs, all cold starts, of a global MPAS in uniform resolution 15 kilometer, but also variable resolution 15 with a 3-kilometer refinement over North America, and doing a number of regional runs. At 3 kilometers, we are running 2 configurations to test aspects of physics. So we keep rotating and updating physics to, keep doing our physics development and testing, but doing an additional configuration to test our smoke, dust, and pollen development. During the hurricane season, we are planning to run again, like we did last year, an MPAS over the Atlantic Basin for tropical cyclone specific prediction. And we're also running daily a 1-kilometer MPAS, and that is mostly to provide meteorological guidance for decisions around fire. So it's called the fire nest, but it doesn't do any fire itself. We've been very happy so far with the forecast that we're getting from MPAS. So here we're just showing a forecast over a period of several days in February. So that's the winter season. It's not the spring season problematic for the FE3. This is composite reflectivity over 24 hours. And we see in this red curve is the HER model with a substantial large bias in reflectivity. And we see actually much better forecast with MPAS. This is not just changing from WRF to MPAS. The HER, of course, is a legacy model from 2020. The MPAS is our brand new configuration with new physics. Another thing that we're very engaged with now is the dropping of the MPAS dynamical core in the unified forecast system. This involves an initial generalization of the UFS atmospheric model so that it can accommodate more than one die core in there. And that is being followed with a connection between the MPAS dynamical core with the CCPP within the UFS, connection of the MPAS with the NOAA coupler, and also connection with post-processing and speed up of I/O systems. And this is what we hope to implement in 2028 or thereabouts. I can't promise that deadline, but that is the target for the RRFS version 2. And we're taking a lot of inspiration about how the MPAS die core or the multiple die cores coexist under the CAM in the CSM model to get our work done. Okay, so switching gears a little bit, I talked before about the UFS, and you may have seen a similar plot, a similar graph like this in Monday's talk by Jacob Carley from the NOAA Weather Service that also had a talk on to you guys. And as I mentioned before, we have a lot of different components and mostly community components that compose the UFS weather system. And here is from the UFS short range weather application from which operational configurations like the RFS are drawn. And so having this modularity brings us this important separation of concerns, the ability to do hierarchical testing or testing components individually and in combination. It brings us ability to do also software testing, like ranging from unit testing to end-to-end workflow tests that combine components. And as we march forward with such a complex user base, it's very important to have also continuous integration and development methodologies to keep absorbing the latest developments in the authoritative repositories and avoid divergence and siloing of applications. Since all these components, or many of them, are community components, it's very critical for us to remain in contact with the community. So NOAA has spearheaded this EPIC, Earth Prediction Innovation Center, which provides support in the code management and software aspects of the UFS, including providing training, etc. So this has been an integral part of our ability to push the UFS forward. As we work with the community, both for NOAA, but as we work with the community, we have to work in a diversity of platforms and architectures. So distributed computing is a necessity. We have to use both on-premise HPC, but also resort, farm out to cloud computing. And the development of a stack that can be used in all these platforms has been a very critical part of our success. And this is done using the spack-stack, so using the SPAC package manager. This is not primarily GSL work. It's mostly done by EMC, JCSDA, EPIC, and the Navy Research Laboratory, but it is a very important foundation to the UFS. As we talk about the use of distributed platforms or a variety of platforms, there is a lot of interest both at GSL and overall and NOAA in the community in obtaining performance improvements with advanced architectures like fine-grained computing with graphical processor units. Of course, we know they can provide superior performance if the code is written accordingly, which is very important for keeping pushing our resolution of the models and also being able to create more ensemble members. So some of our codes, for example, some of our physical parameterizations are already GPU ready using OpenACC. And we know there is a big challenge in terms of which languages should be used for creating the GPU capability for the models. There's many options out there today. We know some options are tied to specific vendors, which is, a concern or something to definitely keep in mind. Other languages may be more flexible as far as platform, but some of them pose a barrier to scientists. We do have scientists used to program mostly in Fortran with some, Python now making forays. But once we talk about C++ or CUDA, that becomes more difficult for scientists to engage with. So we are now starting to work with a GT4Pi, that's a domain-specific language. We already have FE3 dynamical core being ported to GT4Pi by GFDL, and that's another NOAA laboratory and collaborators. And now we here at GSL are working with some parts of our physics. So I don't have any results yet, but that's coming soon. But we did port some of the parameterizations to OpenACC, and we were able to obtain significant speed up. So these are all tests done not in the context of a three-dimensional model, but just with drivers for specific physics. And we worked here in this slide, I show three physics: the Thomson microphysics, the Grell-Freitas convection, and the MYNN surface layer. And we have been generally happy with the speed ups that were obtained. Here on the left side, we have, okay, let's go back. Okay, we have speed ups which we obtained up to 10 or even 14 times. Now, these higher speed ups happen when we use a very large number of vertical levels. Operational models today are more in the range of 100 to 200 levels, but still a significant speed up can be obtained. And on the right side, this is actually a different metric. It's execution time, so lower is better. And for the MYNN surface layer, we've also obtained in the GPU, it's the green bar that you can barely see, a much lower execution time. So we're working with these building blocks and toward creating GPU full versions of the model. So the need for community engagement and distributed computing also poses a big need for community workflows. And we have been working with the development of community workflows in two fronts. So here on the left side of the slide, I'm talking about our work with the federated workflow systems. And by federated, we mean workflows that span multiple HPC systems. So we now have workflow capability to execute a single kind of end-to-end set of tasks involving multiple on-prem high-performance computing platforms as well as cloud platforms. And this can be really helpful. For example, for data simulation, you may want to use on-prem because that's much easier to stage your observations on-prem, but then move to cloud for model integration. We've also been working with a new toolkit that we call the Unified Workflow Tools, which is a set of interoperable and interchangeable drivers to execute model tasks on an end-to-end modeling system. We now use this package to drive both our UFS and MPAS standalone models, and this is a community resource that can be accessed by all. So I talked about wharf-based models. I talked about the UFS that we use for different scales, but that's not all the models that we're using. We're also pushing into high-resolution frontiers because we are interested in fire weather as well as urban scale modeling. So one of the systems we have been using is the GeoFlow, which is developed in-house at GSL, which is our geofluid object workbench, which is not just a model, but it's more of a framework written in C++ to investigate a number of numerical solutions and numerical methods with a target for fine scale dynamics and high order accuracy. It can run on a number of different grids. So it offers a lot of flexibility to explore dynamical core solutions to problems. So this will be very soon GPU ready, and we're starting to connect it to the CCPP for runs with physics. So right now, it does not have any moisture or other physical processes. And within GeoFlow, we're also working to bring in plume capabilities. Here you have an example of a 5-meter resolution simulation on a domain that's 10 by 18 kilometers. So pushing the limits are large eddy simulations, and we're using both theory but also relying very heavily on observations for the development of this new modeling system. But as we are, NOAA, we're very interested in real-time and applications. So we used yet another model called Fast Eddy, developed mostly here at NCAR, I think at the REL laboratory, which we configured with a top at 4 kilometers and used different grid spacings, both 20 meters but also 50 meters. And used a different domain sizes, a smaller domain, 16 by 16 kilometer, 24 by 24, all the way to a larger domain of 32 by 32. And we tried to, what we did was configure this model over airports to see if we if they were viable to produce information for airport operations. So this blue line is kind of the viability line for the configuration. So configurations that are above the blue line were viable in terms of real time, in terms of producing actionable results in a real time with a compute that we thought was applicable to for this problem. And we see that we can, as long as we keep the domain to a reasonable size and stick mostly to the 50 meter, which is those little crosses, we were able to produce information that was deemed usable by the airports. Okay, the last thing I have on this presentation is the work that we're doing on artificial intelligence for modeling. So now we're deviating from the physical models, which we continue to believe are very important. We don't think that the artificial intelligence and data-driven models are ready for tackling all applications yet. They are more mature for global, less mature for convective allowing applications. And we also see a lot of opportunity for cross-pollination between physical and AI models, as physical models are used to train AI models, and physical constraints can be imposed on AI models for better performance. So we are investing right now on both lines of work. But as far as AI goes, GSL now has a draft AI strategic plan, and the top two priorities in that draft plan are to pursue the development of pure AI models at convection allowing scale. So that's the area of the work that we are focusing more resources in. And number two is to develop verification and validation, because in order for these models to be used by NOAA forecasters and downstream users, there has to be trust, and we need to know that they are performing well, not just in RMSE, but in a number of metrics that are important to NOAA. So for that, we have been working on the development of an emulator that's similar to the HER model, but also on a pipeline to train AI models and perform the verification. For the verification, we are using a standalone and very portable verification workflow, which uses the unified workflow tools that I mentioned before, but also leverages the model evaluation tools or MET. And the reason why we're using MET, it's because it is the let's say, official verification package that's a part of the Unified Forecast System, and that is used in NOAA, including in the Weather Service, to evaluate models. So I borrowed a few slides from Daniel. Daniel Abdi already talked yesterday. You may have seen this. So some of this material will be a repeat for some of you. This is a collaborative effort, not only with GSL, but also with NOAA, other two NOAA laboratories, PSL and NSSL. And what we did was use 3 years of HER data to train two models. One is a modified GraphCast model, and it's modified in one way is that it is applicable for regional modeling and not just for its original global, how it was developed. And then we call that model GraphHER. And then we developed in-house a ResNet model, which we're calling the ResHER. And for the ResHER, we have both deterministic and probabilistic configurations. So these models were trained for different lead times, 1 hour, 3 hours, and 6 hours. And then that allows us to roll out forecasts up to more hours into the future. We are focused up to 18 hours. We're working with 6 atmospheric variables at 12 pressure levels, plus 2 surface variables, which are composite, radar reflectivity, and 2-meter temperature. The importance of radar reflectivity here is that it is a proxy for precipitation and is a variable of extreme interest for our customers, especially the Weather Service Storm Prediction Center. And we evaluated in this model over 4 months of runs over the CONUS, and that was for the middle of last year. As far as ensemble regeneration, this was based on the RES-HER using a denoising diffusion implicit model, or DDIM. We used initial Gaussian noise perturbations added to the model to produce the spread. And so far, we are experimenting with 10 ensemble members, but it's very fast to generate more ensemble members. And fast, I mean much faster than physical models, but these diffusion models are definitely more expensive than when we generate just a single model without the diffusion. So here's the CONUS domain that we're using. And this is an example of the radar reflectivity forecast for a given day. So here on the right side, we have the truth, which is the HER analysis of composite reflectivity. No, I'm sorry. On the left side, we have the truth. On the center, we have the forecast, and on the right, we have the error. And the top row is for the deterministic forecast. On the bottom row is for a single ensemble member. And the main takeaway here is that the ensemble member with the diffusion provides a lot more granularity and fine-grained structure. It has less blurring than the deterministic model that does not use diffusion. So, like I said before, we have been experimenting with up to 10 ensemble members. Okay, so I mentioned before about the blurriness, and what we have been noticing is that for variables that are continuous, like in this case temperature, this is 2-meter temperature, we see minimal blurring as denoted here in this power spectrum. So there is 4 curves here. One is the HER analysis, which is our target, and then the 3 models, the graph HER, res HER, and the res HER with diffusion. You don't see a whole lot of difference, so the models do retain at the 1-hour forecast, but also at the 6-hour forecast, they retain their sharpness. However, as we go to composite reflectivity, which is a discontinuous variable, we have more challenges, right? So the HER target is the blue curve. These are the 1-hour forecasts. And we see that the graph HER in red does not achieve the same representation of fine storm structure as the physical HER. And the res HER in green does even worse in terms of loss of energy in the smaller scales. But when diffusion is used, we are able to recover the sharpness. So that's the orange line is much closer to the target HER. And we're very happy to see that even after 6 hours, the ResNet using the diffusion model does not lead to additional blurriness. As I said, we're very focused on ensemble. We think that the power of AI can be most leveraged in the area of ensemble. And this plot here shows our ensemble calibration in terms of spread error. So the ideal spread error skill would be 1, meaning that we have enough diversity, but the members are not just producing solutions that are unrealistic. So 1 would be ensemble envelops the contains the envelope of true solutions. Well, we don't have 1, but physical models, state-of-the-art physical models also do not reach 1. So we're actually very happy with the amount of spread error ratio that we are obtaining. With the different curves here are for different variables. So in red, we have the composite reflectivity, in green, the 2-meter temperature, and then moving on to a number of variables at 900 millibars. And what we see is a tendency of the spread skill ratio to grow in time, which is expected. And in future, we think we can improve this with using different initial conditions. For example, not just the Gaussian noise, but also bringing initial conditions from, say, a global ensemble, adding noise during the denoising steps, and also having even further diversity of initial conditions beyond the global ensemble. Finally, I wanted to mention that in terms of pipeline for training, right now we are these models that Daniel Abdi trained were mostly done with like an in-house homegrown pipeline. But NOAA is trying to rally its efforts around the NMOI, which is infrastructure developed by ECMWF for the staging of data sets, the training of machine learning models, and even the inference or the forecast step of the models. We hope to use not just hope, but we're already using the NMOI framework to read the NOAA data sets and generate AI models to enhance our global ensemble forecast system. And as we go forward, we hope to bring other AI configurations to this framework, both the hardcast that I've just talking to you today, but also our configuration we plan to use for atmospheric rivers forecasting, and the WAFS, which means Warn on Forecast System, which is a very high resolution, high frequency application for severe weather. And finally, we have a lot of focus on this portable mat-based verification. This is work that's mostly done in GSL, because this bigger NMOI effort is actually not so much at GSL. It's more this bigger group of NOAA partners here. But the verification is an aspect that we are focusing on. So this brings me to the end. Thank you for listening. I'm not going to do a recap of all that I already told you, but if you can walk away with just one message, it is that the software engineering is a critical part of our model development and our success. It really underpins how far we can get in this enterprise, both in the physical models and the AI models. And I really thank you all for the contributions that you bring to the community, and it's a pleasure to work with you. If you have any questions, I'll be glad to answer. Thank you.
Thank you so much for your presentation. I think we'll be using Slido again for questions. So if you have any questions, go ahead and drop those in there. Or if you're in the room, you can come up to the mics. And then I guess in the meantime, while folks are gathering their thoughts, I'm curious, great talk, by the way. You talked about a lot of really exciting kind of opportunities and projects moving forward. I'm curious what you see as kind of the biggest challenges and opportunities in terms of like software engineering support for that work that you've kind of laid out here.
Well, I think they are on multiple fronts, right? So, I think there's a topic of languages. Most of our models are written in Fortran. It is very difficult today to find a workforce or new graduates that know this language. We know there's other languages that people are, thinking are more efficient or more, well suited to the Earth system modeling. Like we had a talk on Julia in this workshop, and other languages. But then we face a big barrier in terms of collaboration with the scientists and their ability to develop their code. So that collaboration between scientists and software engineers is definitely, one of the important aspects. I think, it would be, it's always easy to say, oh, a big challenge is we need more compute. Sure. everybody wants more compute, but I think also we need to be more efficient and, really learn how to exploit the languages and the platforms that we have today. So I think this aspect of making our dynamical cores and our physics able to run in GPUs is important. And probably the best way to go forward with that is with full GPU physical model, as opposed to having to farm parts to the CPU and parts to the GPU and having to do all the data transfers. But we're not there, at least not with the UFS and not with the MPAS. So development of these GPU capabilities is definitely critical. And then, of course, in the AI realm, that's so promising and we have so much to explore. And so we just need to get better at, I think we have to get better at the pipeline so we can do this more efficiently. But we also have to get better with these physical constraints to the models. Like today, I think we're still in the infancy of experimenting with that, and that will probably be a key part of making those models better.
Thank you. It looks like we have a question in the room. You want to go ahead?
Well, thank you so much. Really, really interesting talk and a lot of interesting efforts going on. So I was wondering, what has your experience been in, and overall your consideration in adopting modulus for the AI frameworks at GSL, and overall what has been the experience? It seems like modulus is mostly built with ECMWF infrastructure in mind, but yeah, so I was just wondering what were the consideration and overall experience in adopting modulus and deciding that would be the framework to adopt.
Well, we can't do it alone. I think that's the main consideration, is that we need to partner with other organizations and leverage what is already existing in the community. Personally, I am not aware of any kind of bake-off or comparison of different systems that were potentially available. I think we do have a collaboration with ECMWF. They were, of course, pioneers in this effort, and have now operational AI-based global model. So due to the collaborative, I'm not able to speak to the software engineering aspects, more to the programmatic or collaboration that we have with them, which made it very easy for them to provide training and get us spun up with the system.
Yeah, that sounds great. So was it easy to adopt it for a new HPC infrastructure and a new data infrastructure that you have at GSL?
So as I mentioned in that slide, GSL is not the primary group that is doing the implementation of the system. So EPIC, the Earth Prediction Innovation Center, together with NOAA Physical Systems Laboratory, are the two groups that are mostly hands-on with that system. I am aware that we now can operate the system for training of global model. So
that's great. Yeah.
So I don't know if it was easy, but it was possible.
That sounds great. Thank you so much. Thank you.
It looks like we have a couple of questions online as well. Yeah, okay. It looks like Dan will ask his in person.
Yeah, I can say mine in person. So in terms of hesitancy from scientists and
Could you come a little closer to the mic, please?
in terms of hesitancy from scientists and RCs on choosing a GPU programming paradigm that you mentioned, what do you recommend are better practices for navigating these discussions so that we can more readily move forward with GPU porting efforts? How do we then manage pain points from varying levels of compiler support?
Yeah, right. I don't have, I don't know what the answer is. besides that we need to keep talking, and we cannot implement the solutions one-sided. I think that it would be very important to bring both software engineers and scientists together to find a common solution. So I think we just need to have more discussion on this topic, and with diversity, people with multidisciplinary, so both scientists and software engineers. And I think it would be good to have multiple organizations discuss this, because, for example, we develop physics that are used by a number of models, right? So if we adopt a solution, it needs to be usable in multiple settings. So I think some forum to discuss that would be very interesting to set up.
Thank you.
All right. And it looks like we have one more question online. It says, great talk, thank you. I'm curious about the interoperability between the software codes. How did you accomplish this? Is it one person doing the interpretation between the interfaces, or was it driven organically among the various developers?
Okay. Well, interoperability does not come naturally. It has to be very intentional. So I think it's been since the 1970s, at least in the area of physics, there was a very important seminal paper published by Eugenia Calne in the Bulletin of the American Meteorological Society, putting forth the paradigm that if we developed with interoperability, we will make progress faster. But when you're actually doing the development, it is not faster. If you develop an interoperable way, it is faster if you just put whatever solution for your problem of the day. So I think it required a lot of intention. So for the CCPP, for example, we started at the beginning with lots of discussions between NOAA and NCAR. Actually, we had software engineers both working at NOAA and at M-Cubed devise the initial solution, which then has been refined. For example, when the Common Community Physics Package was being considered for adoption by the CAM-CIMA, atmospheric model of CESM, we had actually to revise some of our requirements and coding plan so that it could meet all their requirements. So it's not a one-person job. I mean, in the end, you may have, lead developer, but it has to be agreed upon. And we have to, collect the requirements and try it out and keep evolving as the development happens.
And it looks like one more question in the room.
Yeah, thanks for the talk. I was curious, thinking about interoperability with CCPP in particular. There's a lot of talk just in general about using, I guess, like AI physics emulators in place of physical parameterizations. Has there been any thought in terms of how those could hook into CCPP, or would that sort of be out of scope?
No, it would not be out of scope. So today we already have some aspects of AI working in the CCPP, but none of them are part of the public release or the authoritative code. So we have AI development in sub-processes of both convective parameterization and microphysics. And then in terms of full replacement, we have a machine learning emulator for radiation. So it emulates RRTM. There is no limitation. I think one consideration is that some of these emulators rely on other, like, third-party libraries to work. So that does bring another kind of level of dependencies into the system, which may kind of, well, complicate or add complexity to the installation, especially for those that are not seeking to use those capabilities. So I think that's one consideration that we need to think. Every new library we bring into the system, we should be very careful. Also because the acceptance of new libraries by NOAA central operations is a very steep curve. You know, they are very conservative there.
Thanks.
Okay, it looks like one more question, and then I think we'll kind of wrap it up here.
Ligia, thanks so much for your talk here. I was really inspired by a lot of the modularity you're bringing in and the interoperability and all that, and that's awesome. I'm just curious where this idea started of going down the path of UFS, and how it took hold and came about and all that kind of thing.
Well, so I think it started when there was a number of programmatic reviews of the NOAA operational production suite. So NOAA themselves commissioned a number of experts, and they came from different walks of life. They were from NCAR, from universities, and from operational centers at other countries to evaluate that production suite. And a big recommendation out of that, it was like, simplify. You have too many systems, because there was the WRF model with the ARW and the NMM dynamical core. There was the Spectro GFS. There was the NAM, which is, that uses the NMMB dynamical core. And then as far as physics, there was a lot of diversity that was unintentional, and separation in the code base. And then even things like the post-processor, pre-processor, to get data, etc., was not the same for all these modeling systems. And that creates a huge overhead in development and maintenance of code. So I think it started from there. And then one of the next steps was, okay, so which dynamical core should we use? And then there was the bake-off. I don't know if you remember that, but there was a number of 6 dynamical cores, let's say, competed. There was a set of tests that they had to take, and then the forecasts were examined both in terms of meteorological accuracy, but also computational performance. Out of that exercise, 2 die cores survived, which was FE3 and MPass. And then more tests were done, and the MPass group ended up not continuing in the exercise, and the FE3 was the one that remained and was therefore selected. So, okay, so now we have the dynamical core. And to do that bake-off, the same physics had to be put in the MPass and the FE3 model. So then this one thing called the interoperable physics driver of IPD was created back at that time, which we then later kind of generalized, expanded, and revamped to make the CCPP. So the idea of the CCPP was not just the framework and the software, like how we're connecting and doing the metadata and the caps and all that, but just the idea of having a single code base with well-organized code management that people from both short-range weather, 3 kilometer, all the way to seasonal can pull from a single code repository that's, transparent and maintained, and we know what's going on. That was considered important. So I think that's how we came to pull these modules in.
Yeah, thank you.
you so much. Let's go ahead and thank our speaker one more time.
Thank you so much.
So much for being here today. And then just a quick reminder again that we'll be starting back up at 10:20 after the break. So if you have a older paper copy of the schedule, you'll want to look at the one online for the most current state. And I believe there's coffee and snacks outside the break. So I didn't misspeak. Still bored.
But yeah, we sure that the old system is
Common
Caught left,
challenges across agencies were like maintaining. I mean,
Yeah, it's been run. Give me one.
Okay, good morning, everyone. So I think we have 1 minute left to the next session, so it's a good time to start at least introducing myself and the session information. My name is Orhan Iroglu, and I work as a software developer and team lead in the Computational and Information Systems Lab at NCAR in Boulder. Today, I will be helping moderate this session, in which we have 5 presenters. I will be keeping track of the time and making reminders in the maybe last 5 minutes to give you a time to wrap up and then have some time to questions as well. I am very pleased to welcome our first presenter, Don Heinzeller, who works as a computational scientist at the United States Naval Research Lab through a contract at ucar-sea. Thank you for coming, Don.
All right. Thank you very much for the introduction. I hope you can all hear me. Thanks for being around for this whole week. It's been a long week. We're all pretty tired. Thanks to the organizers for giving me this opportunity to talk to you today about spack-stack and what it did for us with the Neptune operational transition. My colleague Alex Reineck here is co-author on this paper, is also the PI of Neptune. I wanted to mention that. And I will also stress one more that it's really important what we are doing. Brian mentioned this in his opening statements. The weather forecasting products we develop at the Naval Research Lab are transitioned directly into operations. They're used to defend the country. They're used to protect the sailors at sea. Now, this is a military side application of weather prediction, but it is really important. So there's an immediate impact of what we're doing. And so hopefully here I can show you that the infrastructure side of things is just the foundation of everything else that builds on top of it and plays a critical role here. So you probably haven't heard about Neptune because it's not an open model. And I wanted to give you a little primer here. Neptune is the Navy next generation global modeling system. It's replacing the current NAVTIM operational system that's been in place for more than 10 years. And it's getting old and needs to be replaced by something newer that is more future-proof. And so because Neptune is sort of a clean start, it provides you with some features that are cutting edge, both in terms of science as well as software engineering. And an example here is the Neptune numerics. So the numerical solution in Neptune is represented by a local polynomial expansion on top of a spectral element mesh, which means as opposed to other models where you have only one way to achieve the grid resolution you want, here you have two. You can increase the number of spectral elements, or you can crank up the polynomial order. So that gives you excellent scaling and also provides you with dense floating point computations if you think about accelerators. The Naval Research Lab is relatively small, at least compared to NOAA. So we can do everything in-house, and wherever we can and wherever it makes sense, we try to use community code. So very much like the UFS, we're using the Common Community Physics package, currently version 6 in Neptune. And we did a lot of testing of Neptune as we ramped up for this first operational implementation. So Neptune in operations will be run at 9 kilometers resolution. That's the Scriptic E96P6 resolution, 104 vertical levels. And this first transition is without any updates to the data assimilation. So we are using NavGem, that's the current operational one, hybrid 40-bar initial conditions. And so we did a lot of testing, year-long forecasts, and iterative process, many CPU cycles spent. The package that's being delivered into operations is the Neptune system or Neptune ecosystem. So this is in 2025, it's happening now. The Neptune atmospheric model consists of the numerics, the dynamics, the time integration, and the physics. Then we have coupling infrastructure that's facilitated with ESMF. So Neptune acts as a NOAA enabled component, and then there is asynchronous I/O. And on top of that, we use ESMX as the driver. That's the Earth System Modeling executable, a relatively new addition to ESMF. And the workflow is controlled with the Silk 8 workflow engine developed by NOAA, UK Met Office, and so on. I mentioned data assimilation. So this first operational implementation is without any updates to DA. The next implementation is around the corner. It's only 2 years down the road. And that will bring in the Neptune data assimilation system Falcon. That's basically Neptune coupled with JEDI, developed by the Joint Center for Satellite Data Assimilation and its federal partners. And that's also a hybrid 40-bar DA system. All right, so transitioning innovations from research to operations, or this R2O to R cycle, is something that's been a problem for the US weather enterprise for a very long time, to the point that it's been given the name the Valley of Death, and there have been comics that people drew about it, and there have been papers. So Neil Jacobs, former NOAA administrator, wrote one for the UFS about that. And I wanted to take this little picture in a few minutes to, set the scene a bit from how this affects us from the software engineering side of things. So we, the Neptune developers, we prepare our little package, little, it's not actually that little, for operational transition, and we work on a certain system with a certain software stack. In parallel, the Neptune plus JEDI developers work on their next version of the code that brings in the JEDI system with a ton more external libraries and dependencies and requirements, and they might be using a different machine and a different software environment. And then traditionally in the past, we'd be packaging all the stuff up and then tossing it over the fence and telling FinMOC, that's the Fleet Numerical Meteorology and Oceanography Center, so the operational arm of the Navy. Okay, good luck. Here's your package. Here's a little README. By the way, you need to build those 300 packages in order to run this thing. And that didn't go so well in the past. So we decided we need to do things differently, especially because 2 years down the road, we'll have twice as many dependencies going into the next transition. So we decided to engage in an effort called spack-stack, and it's been mentioned several times here. It's a joint effort and interagency collaboration between the JCSDA, NOAA Environmental Modeling Center, EPIC, and NRL. And we also have two partners who make increasing use of it. So that's NASA and the UCAR Developmental Testbed Center. They haven't really engaged formally in that collaboration yet, but we hope this is going to happen soon. And if that happens, then we have a significant portion of the US weather enterprise represented in that collaboration. So the idea here is to provision unified software environments that work seamlessly across HPCs, cloud platforms, macOS, and Linux laptops. And the promise is that spack-stack makes it much simpler to deploy and develop all these components, whether that's Neptune, JEDI, UFS, MPES, GEOS, whatever you have. And we do this by using community code SPAC under the hood, as you might have guessed by now. So we heard a lot about SPAC yesterday. Don't need to go into details here, but if you missed that talk or you forgot about it, so SPAC Supercomputer Package Manager, originally developed by Lawrence Livermore and now part of the High Performance Software Foundation for Linux, is a project that brings in the force the power of the community by sort of separating the concerns. Lawrence Livermore takes care of the core SPAC engine, the API, and the overall direction, and they review pull requests. But all the package recipes, so how do I build HDF5 with this version of that compiler, those ones are contributed by often the package creators or by the community, otherwise people who want to use this package. And so the point I'm making here is that we as the Navy, but even together with NOAA and NASA, we just don't have the capacity that we can continuously update build systems for hundreds of packages, 5, 6 different compilers, each of these compilers with new releases every year. So that's just impossible. And so the chances are high that when we get to the latest version of HDF5 and the latest version of the Intel IFX compiler, somebody in the community already figured out all the bugs and contributed those changes back to SPAC, and then we can just take that and don't have to do it ourselves. So this question came up on Monday or Tuesday, I think. How do we deal with Python and SPAC? And it's one of the big assets for us as developers, but especially also for operations. SPAC handles Python packages correctly, at least a ton better than many other solutions out there. So the reason this is because SPAC usually builds its own Python with the compiler that you tell it to use for that. You can also tell it to use an external Python, but it's really recommended to let SPAC take care of this whole thing. And then when you have your so-built Python, then you build all your dependencies that you need for all these Python packages, also with the compiler that you want, with the options that you want. And so when you end up with something like PyNetCDF4 that is built by SPAC, it will use your Python and it will use your NetCDF with your compiler and your options baked to NetCDF, whether that's quantization or the latest zlib compression and whatever else. And it's even more critical for compiled components like PyNumpy, where you have an extension that you need a compiler for too. So rather than being at the mercy of some developer who puts out a wheel of PyNumpy with whatever compiler they decided to use, I can compile PyNumpy with my version of Intel and I can use my version of Python with my version of netcdf that has exactly the features that I need. So again, speaking from an operational point of view, SPAC is secure and works on air-gapped systems. That's obviously a big concern if you think about operations, especially for military purposes. SPAC offers you the option to use mirrors, that is also called source caches, and it was mentioned yesterday, so that you can install the whole software environment on an air-gapped system without access to the internet. And the way this works is that you take your environment, and people who were here yesterday know how this works, go to that machine, and then you concretize and solve the dependency tree. You take that resulting spec.log file, put it on any machine in the world, can be a cloud gateway, whatever it is. It downloads all the packages, and then you transfer these tarballs over, and you can install from that. Another important aspect is the support for build caches for fast installations. So SPAC can store compiled packages in a binary cache or build cache, and then reinstall from it. And the way this works is that it creates a tarball, and then when it installs this tarball somewhere else, it extracts it, and it goes into the ELF headers of the libraries and the binaries and whatever, and in the R path, and substitutes all of these with the correct final destination. That's the relocation step that was mentioned yesterday several times. And it does so only if your package hash is 100% the same, which means that all the input requirements, all the dependencies, all the build options, everything is identical. So this makes installing environments extremely fast. You can install hundreds of packages within minutes. And there are many use cases for this. For us specifically, we can compile packages on one machine and then deploy it on an identical machine. If you remember Jacob Kali's talk on Monday, where he talked about the WCOS2 twins, so the operational, the backup, you can run your forecast on the operational one. The backup can be used to, continuously build new versions of the software stack so that whenever you need one, you can deploy it. We can also prepare environments as one user and then install as another user. That's pretty useful for many applications. And it helps with CI testing, continuous builds overnight. You don't want to build the whole thing that takes 12 hours for each compiler overnight every time. But if you can only build the delta that changes due to commits from the last day every time, then you can keep the system running. And whenever you want, you can just say, hey, deploy this thing as a click of a button, because it's all there in the build cache. Just go and extract it. So why spack-stack if SPAC is so great? Well, you know the answer if you listened yesterday to the SPAC manager talk. SPAC is simple, but it's not entirely simple. It's still a new tool to learn with many, many features and options. And it's also by purpose held general. So what we've seen over the years is that every group that gets more involved and more serious about SPAC starts developing some sort of manager around it to manage your specific needs, whether that's simpler workloads, or providing specific documentation to your system you need, or storing those site configurations, compiler configurations, packages, which environments do you want to build, and things like that. And then adding test harnesses for CI. And that's what spack-stack does. So just like SPAC Manager, it's a thin wrapper around SPAC that builds on the SPAC extension functionality that's baked into the system to do exactly what we need it to do. And so returning to home base here, we made this deliberate choice that it's either going to be spack-stack all across, or we might as well just not do it, because otherwise it's just one more of many solutions. So all across the Naval Research Lab, wherever we are concerned with transitioning something into operations now or in the future with Neptune, is spack-stack. So the latest release of spack-stack 191, we installed on all the available platforms that we have, so the DoD HPCMP systems, Blueback, Narwhal, and Nautilus. And we typically roll out several environments. There's a Neptune standalone environment. I need to explain what that means. We have a unified environment. That's the big infamous one that can build everything under the sun: Neptune, Jedi, MPAS, UFS, GEOS, DTC, SCM, you name it. And we also have a Silk environment specifically for driving workflows. And typically we support a number of compilers. And I will note to Damien here that we hope to add the LLVM compiler in the next release to that, at least for a subset of these environments. The point I'm trying to make here is that one of the strengths about spack-stack is that the way you use it, the way you load it, is always the same. It doesn't matter which machine you're on, which application you're trying to build with, it's always the same. And that consistency has been a big game changer for for all of us, all of the partners. So if you look at that little code snippet down there, first we sanitize the environment. Every user has to start with a clean plate. And then you just use one module path, which contains a number of sort of meta modules, we call them stack-compiler, stack-mpi, stack Python. And then you can either load a virtual environment that contains everything that you need to build something. So if you don't worry about specific versions and just, hey, I want to build Neptune 1.5, give me everything that I need for that. Or you can load individual modules. So the yellow parts change depending on which system, which version of spack-stack you're using, which environment, but everything else always stays the same. And so not only on the development side, we also decided at the Navy that we are going to do this for operations because we want to, resolve these problems that we've seen in the past over and over again. So we took the spack-stack 1.9 release and we created a dedicated release Neptune 1.5.0 specifically designed to support this transition. And so this is a trimmed down set of compilers and environments, as you can see here. But you will note that we are running that on the same system for now. And so there are a couple of big wins by taking this approach. The first one is that we were able to package up spack-stack 1.5 and Neptune 1.5 as two separate releases, and then give those to FinMock well within the agreed upon deadline, actually 12 hours ahead of the deadline. This is like years in terms of what we usually do. FinMock, that's the operational arm, just to remind you again, they were able to take our spack-stack release and the instructions and then compile these environments from scratch within a few days, or also do that from our binary caches. So the first one is the longer one, but it demonstrated to them that they can do this themselves if they want to. They can store all the build logs, or they can just take our binary cache and be done within minutes. So what we also try to do here, and it worked well so far, is to engage in frequent feedback between the Neptune developers and then the FinMock operations side of things. And that's really important. It's hard because this is not how people used to work in the past, and you really have to remind yourself and force yourself to do it every time. But it needs to be done, and we try to do this in the open. We try to put this in our GitHub space so that all these conversations are recorded somewhere and not just some chat message or an email here or there or a hallway conversation. But as a result of that, we're hoping to have the 1.5.1 tags for spack-stack and Neptune available soon. And with a bit of luck, those will be the final packages going into ops. I will also mention that one of the big wins was that the Blueback system that I mentioned a few times beforehand is actually a brand new system. It's still Pioneer access. But once we got Pioneer access to that system, we had Neptune plus Silk, the end-to-end system, running within 24 hours. So for a period of weeks, we had the system for ourselves, basically. So spack-stack is a powerful tool that greatly simplifies the transition of Neptune to operations in our case, but the same can be said for NOAA. It's tremendously helpful for us that for this first operational implementation based on spack-stack, we will be operating on the same machines, albeit separate fenced-off partitions. And that close collaboration and frequent feedback between research and ops can't be stressed enough. I wanted to leave you with a few thoughts about challenges, and I picked only one of several because this is sort of relevant for the software engineers among us. Spack and spack-stack by extension is sort of a bit different from historical approaches because we kind of cut deep into that HPC admin territory by trying to build everything from the scratch up. Basically what Spack says, give me some sort of compiler and I'll take it from there. Maybe an optimized MPI library on top of that, but the rest I'm going to take care of myself. And so whenever you have something that provides you with an environment for an elevated user experience, like the Cray software environment or custom software environments, that makes our life difficult. So Cray, when you go to a Cray, you load the Cray programming environment, you get the Cray wrappers, the Cray libraries, whatever else, and that's problematic more often than not. HPE has recognized this situation. They are working actively with Lawrence Livermore to address this problem. So if you go to their website, HPE, Spack user documentation, you will find that it says it's recommended that any compiler be invoked without the Cray programming environment compiler driver. So go directly to iFort or whatever else you have. So good, this is being addressed on the Crays. The bigger problem for us is if HPC sysadmins do this locally in their systems, because then it becomes much less consistent than when you go to a Cray. You find the same sort of Cray stuff everywhere. So people put their own workflows on top of that for making it easier for their users on their specific system. But at the end of the day, I would argue it's not only hurting us, it's also hurting those users, because when they need to take their workflows and go to a different HPC, and in today's environment, we have to be able to move from HPC to cloud to other systems. Suddenly things fall apart because that little piece of convenience that I had on my HPC I started out with is no longer there. So therefore, at the pitch, my sales pitch here at the end is that at the end of the day, I believe it's best for everyone if we adhere to common industry standards and provide our users with the system that we are given, provided by the vendors, and support that to the users as is. So when on the DoD HPC systems, for example, we don't have this problem. They took this hands-off approach, saying, if you want something else, we go back to the vendor, let them install this, and then provide it to you as part of their solution. And that's what I have. Sorry, I'm running out of time. So hopefully we have time for a question.
Thank you very much, Don. We can take a quick question.
Yeah, thanks for the talk. That was great. One question I had is, you said that spack-stack is being used by Neptune and it's being used by UFS and others. How do you coordinate when one project wants to introduce a new dependency or a new version of a dependency? With that, how to keep that from breaking for a different project?
That is interesting. So it's been not too challenging so far because weather prediction systems sort of have a big overlap in dependencies, but usually it just starts with, okay, you create an issue here, you tell us what you want and when you want it to be available, and we'll try to accommodate it to the extent possible. And so far we've been able to get everything into one unified environment with a gigantic number of packages. We had to take out Silk into a separate environment for these reasons, because Silk has conflicting dependencies with others. And so we have to sometimes be innovative and come up with solutions around that. But we'll try to make a best effort. And so far, everybody has been really cooperative because everybody's benefited more than they've given up.
Thank you very much. And please join me in giving Don a quick round of applause again. And it's my pleasure to welcome Carol Ruchti, who works as an associate scientist at NCAR Earth Observation Lab.
Great, thank you, Orhan. So I'm Carol Ruchti. I'm an associate scientist. As others have introduced themselves, I'm not technically a formally trained software engineer, so I really appreciate being able to talk at a conference like this and learn more about software engineering. I work here at NCAR at the Earth Observing Laboratory, or EOL, specifically within the Data Management and Services group. Today, I'm going to be talking about modernizing our product generation for our field catalog tool. So first, I'll talk about some background. What do we do at the Earth Observing Laboratory? We provide end-to-end observational expertise dedicated to facilitating research of the Earth's atmosphere. So that usually involves supporting field campaigns, which are often these larger scale science studies that can happen all across the globe. There on the right, we have a variety of different instruments that the PIs can request to use for their field campaigns. Within my group, the Data Management and Services group, we provide two main tools, one of them being the EOL Field Data Archive. So you can think of that as post-field campaign data collection. I have these little hearts here. You'll see lots of emojis. I'm a millennial, so they'll come up here a lot. But the Field Data Archive hosts file formats like NetCDF, archive, iCart, CSV, those kinds of things. But the tool I'm going to be talking about today is the EOL Field Catalog. That is a data visualization tool that's used for real-time operations during a field campaign. And I like to think of the field catalog mostly focusing on images, like JPEGs, GIFs, and we also have a maps tool as well that uses KMLs. And yeah, like I said, it's a real-time operational service that is used during the field campaign. So what does the field catalog look like? If anyone is interested, I have the URL up here. This is for a project called Snow Climb that's currently happening in Steamboat Springs. This is what the homepage looks like, but I'll mostly be talking about products that would sit within this tab here. But yeah, the field catalog is a very widely used tool for most and every UL field campaign that occurs. I had a video here that shows our maps tool, but maybe it's not properly loading. Anyways, there's also a map tool that provides KML information. It can do flight tracking, things like that, and it pairs very well with these products that we're going to be talking about. So I'm going to show some examples of what is a typical field catalog product. Those can be satellite products. This is a image over Argentina that we used for a project from a few years ago. This is what I'm denoting as an EOL generated product, meaning that I'm making this product from the raw data files to make the plot. And there's other cases where you'll see in a second how that differs. In this case, this is a web generated product. So this is just an image that I'm pulling from the internet. This is a SKU-T, a common product that's used for field campaigns that provides vertical profiles. Specifically, this is from Albany from a project a few years ago. We also generate model products. So this is a very specific case for an Arome Arctic model that's only a 2.5 kilometer grid that really is only over kind of the Scandinavia, Svalbard, east of Greenland region. But this was used for a project last year that we did out of Sweden. This is a 850 millibar relative humidity plot that we can make more specific kind of flight tracks if we use the raw data files to make these plots. And then for the current project happening at Steamboat Springs, this is the sea-pull radar from CSU. This is a web-generated product, obviously generated by those at CSU, but I'm just pulling it from their web server. And that's another kind of product. Finally, we have KML products. One of my favorite KMLs that I've made, referencing cattle and dairy lots that are near Fort Morgan. Used emojis here again. And additionally, within the mapping tool, since the map didn't load before, these are what like the real-time flight tracks will look like when there's a plane doing a field campaign. Okay, so I'm going to talk about the need for software redevelopment of these catalog products, my plan for redevelopment, and I'm going to prove to you that, well, hopefully prove to you that the redevelopment was worth the effort. So a few more statistics on the catalog just to get a reference of how many products we're really talking about. These are all estimates here, so take them with a grain of salt, but we host something like 5 field catalogs every year. Each catalog is maybe up for a 4-month time period. I can very roughly estimate it can be very high or low compared to this number, but something like 2 million products are generated for every field catalog. That equates to something like 16,000 products generated every day. So the Perl repo that has been used for the past 30 years has been very, very successful. But these are a few more statistics on what that really has looked like. So the repo is quite large at 2.5 gigabytes. It's over 5,000 files. Those files are divided by staff name and project name, and the scripts and files are often only differing by maybe something like 5 lines. And it was pretty easy to tell that there were often keywords that could have just been saved in, let's say, a configuration file to make that a little bit better. And the development workflow was really just committing to main within our GitHub repo. And so I had this idea of thinking of a better way to do product generation. And so in comparison with this Perl repo that was a bunch of unique scripts for each field campaign, I wanted to create a new Python repo that was more of a shared code base that was object oriented. And here we go with the emojis, they just continue. So yeah, maybe as you can tell, I have a pretty big passion to make the catalog as as wonderful as it can be. So I wanted to work on this repo and make something a little bit more efficient and better and easier for me to use. I had some pretty clear ideas of what I wanted the repo to look like, but I also needed to get buy-in from the catalog team such that they also agreed that doing this redevelopment effort was worth my time. And as I said, since I'm not a software engineer in training, I really needed to work with a mentor. So I was able to work with Eric Johnson, who's a great software engineer in my lab in EOL. And so to kind of get at what my ideas were, I was pretty strongly moving towards moving to Python. That was the programming language that I knew best. I wanted the code to be much more reusable. There wouldn't be so many duplicated scripts. And I wanted to not only learn, but create a better workflow within GitHub in development of these product scripts, or yeah, of these products. And then, as I kind of alluded to before, I had a really strong vision of what would be required within the configuration files. I had a good idea of which keywords would be necessary. And then I wanted to tap into more Unidata resources, including referencing the thread server to get real-time data, and also using more of the MetPy Python library. And yeah, finally, I wanted to really re-emphasize trying to make these products from the raw data files rather than pulling images already generated on the web. So to start my work with Eric, he emphasized creating these milestone documents, creating a scope for this project, and even writing software requirements. And he promised me the software requirements were already in my head. I just needed to write them down, which was true. And so it was great to kind of create this formal documentation for my first software engineering project that I was leading myself. And so in working with Eric, we started working in almost 2 years ago in June of 2023. We've been meeting monthly or biweekly, which has been really helpful. And he's been able to provide a ton of different resources. He's been able to review my code and really be a great reference and sounding board for a lot of great discussions. And so once I had enough information to start this on my own, I just kind of jumped into it, made a lot of mistakes along the way, but I eventually really did learn object-oriented programming properly within Python, and I grew a much greater appreciation for understanding how to do proper GitHub workflow in creating issues, merging branches, and all of those things. All those things you're all probably very good at, but I had learned in the last year or so. So what do these configuration files look like? They're pretty simple. This top section within FC product is really related to what's required to make a file name, and a few specifics related to each of the project names or field campaign names. And in the case of just pulling an image from a web, all you really needed was the URL and the file name. So it was great to develop these, and nice to see how simple they ended up being. And so this kind of gets at the class structure of what I ended up creating. So these products will reference back to the original products that I showed at the beginning of the talk, but I created a FC product class to begin with. Then I made these web product classes as well with various methods. I needed to create an FC product grid that could pull in the gridded data that I was very passionate about trying to create these gridded products. And then also from the gridded product class, I needed to also make some methods specific to plotting GOES data. And then I also made a pretty quick FC product KML class as well. This is just to prove to you that I really did do it. Here's some references to the actual code of the init scripts of what the classes look like. In the case of FC product grid, you can see there's a lot more keywords that need to be related to referencing lat, lon, center points, and what variable you're actually going to be plotting. And so I'm happy to report the current stats for the Python repo. It's 7 megabytes. It includes 4 startup main scripts. It has 6 different class files with various class methods and 1 dictionary file that mostly references information required for color mapping. And as I've mentioned, well, as I've referenced before, these configuration files are really important, and they are saved within the repo, which might be a little bit unconventional, but between myself and the catalog team, we really wanted to keep that history within the repo to be able to really quickly reference it. And I really tried to write very good detailed documentation. There's been a lot of talks, like I know Tori mentioned this in her talk as well, to really emphasize making good detailed documentation to begin with. And the code has been running for roughly 1 year in operations with the catalog. Different versions have been updated, but it's been pretty successful so far. And to just throw these numbers back at you, something like 1% of the number of files are in the new Python repo, and the size is only 7 megabytes compared to 2.5 gigabytes. I will say, as I emphasize down here, I can't say that 100% of the capabilities of the old Perl repo have been ported into Python. I wasn't going to look through 5,000 files to verify that, so maybe something like 90% of the capabilities have been ported into Python. And yeah, just in future work, I want to add more testing, better error notification if a product isn't available for whatever reason. I'll continue to write more Python classes as I learn new products that might be needed for the catalog. And as I said before, minimal web products. I think really want to move away from that as we go into the future. And if I can make one reader for the main script, that would obviously simplify things a lot more. And yeah, continued learning of software engineering. And I just want to say again, it's been great to be at this conference. I really appreciated what Brian said at the beginning of the day today. And yeah, it's been super helpful to engage with you all and learn more about software engineering this past week. So thank you very much. Happy to take any questions.
Thank you very much, Carol. We have time for multiple questions.
Yeah, I have a question. So I love this idea of partnering as a scientist with a software engineer, and I'm wondering what kind of hurdles you had to overcome to get Eric's time. I know you had to justify you wanting to do this, but to get that collaboration going.
Yeah, great question. I know Eric's online too, so shout out to Eric for being a great mentor. But I think that it helped that Eric was obviously on my team and worked within my data group. But I will say, I think it required me talking to my supervisor, Eric talking to his supervisor as well to justify the effort that Eric was also going to put into mentoring me. And yeah, I think I would just really encourage folks, if this is something that you think is available to you, make sure you talk to your supervisors about potentially working with someone more closely like a mentor. It's been really valuable for me. Thanks, Janine.
Yeah, I'll follow up on that. Not that it should be like your responsibility or Eric's responsibility to advertise that idea, but I wonder if anybody has sort of talked about how successful this model sounds like it was to EOL leadership or even higher up, because I think it's a great idea. I'm sure it happens from time to time informally, but it'd be great to have like a formal structure to get enthused non-SEs to work with SEs.
Yeah, a few thoughts. I mean, I know that UCAR or NCAR host their mentoring program. That's a much more formal setup that Eric and I didn't necessarily want to get into. But I think, I've tried to emphasize, at least to my lab leadership, that maybe not this example of Eric and I working together, but the idea that everyone should feel like they can be empowered to get a mentor or at least do some kind of career development. I don't know how successful I've been because it's only been one discussion, but no, I think you bring up a great point of how can we advertise something like this more within NCAR or broadly within other institutions. So yeah.
Yeah, I'm going to bring this up in the SEA because I think that's a good vehicle for it as well. So
Yeah.
Thanks.
Thanks.
I think I have a quick question, Carol, as well. So I believe maintaining lab level data should be a very hard job, and I'm also aware of other NCAR data archiving and cataloging services like Research Data Archive and also the pivot to data commons as well. And also there are outside NCAR data services and archiving efforts as well. Is there any collaboration between like your lab and others to some level?
Yeah. Now you're going to ask me a question about the archive specifically, which I'm not always as good at talking about, but I think, yeah, there's definitely efforts working with the RDA and other labs within NCAR to, yeah, potentially move our archives together. I think that remains to be seen how that really is going to pan out, but discussions are happening. Yeah.
Yeah, thank you. And let's thank Carol again. And let's move on to our next speaker, who is
Excuse me.
Daniel Madren. Daniel works as a program manager at the Purdue Research Computing team. Daniel, take it away.
Hello, everyone. This is going to be rough. I have to follow Carol. She's brilliant. All right, so let's go ahead and get started. So as he had mentioned, my name's Daniel. I'm a program manager for research software engineering at Purdue. Just to give you an idea, the size of our team, we have roughly 90 employees, touching everything from HPC to research software engineering. But the RSC Center specifically, there's about 25 to 30 employees. So just a little introduction. So RSC projects, as we know, they really sit at a crossroads between innovation and heavy interdisciplinary collaboration. So this often leads to management chaos. Some common pain points that you might see in an RSC project would be, misaligned goals. So with multiple groups having different success criteria, it's unsure if that is documented or not. Miscommunication. So, faculty request or research groups requesting features without actually specifying those requirements that could lead to rework. And scope creep is very common, especially in research and discovery. When an RSC does a really stand-up job in something, then a faculty member says, oh, you could do this too. And that's not the best approach. Lack of documentation, so dealing with legacy code, when a graduate student leaves and you have to go back and really figure out how do you replicate that. And then another thing is just scaling those efforts. So a lack of standardization, a lack of business process kind of barricades the scalability of a research software engineering center or a group per se. So there's a unique challenge here. There's not much of a formalized structure across different groups. And with research uncertainty, there's shifting requirements and these demands across these projects. And then the last thing is just these grant funding cycles. There's inconsistencies in that. So really figuring out how do we support our RSCs in their sustainability and in their code and in their work. So why does structure matter in research software engineering specifically? So the benefits of structure and providing structure for RSCs is it improves collaboration across different disciplines. And I've seen that in our team. Traditionally, our RSCs were rather siloed. So being able to kind of pool them together across different disciplines within not just our team, but our organization has improved our efficiency. So another thing too is it enhances our product reproducibility. So if we have documentation, it's something we could pass on to another group. Let's say somebody leaves our group, then we actually have something that we could fall back on as kind of a cheat sheet for our code. And then another thing is minimizing these inefficiencies across the group and reducing technical debt, which I'll touch on later. So the cost of ad hoc project management, what traditional RSC is, there's a chance for wasted time and resources, frustration among those stakeholders, as I had mentioned earlier. If there's different success criteria across the different groups, there's not really a cohesive synergy there. You need to be able to document that. And then it's much harder to scale and even onboard new employees if there's not kind of a standard way of doing things. You need to have a common mission, vision, goals to be a true team. So I propose a flexible hybrid approach. I'm not just saying, oh, predictive project management, we have to plan everything at the very beginning. No, absolutely not. That is going to lead to even more chaos. I think that hybrid is the best approach because you get to mix the best of both worlds. You can mix agile and waterfall. And that's exactly what I did with my RSEs. When I came in last year, we sat down together and we said, well, how can we prevent this scope creep, this isolation that we're feeling? How can we work together to have better documentation? So With waterfall, you're able to have more of a long-term planning approach, but at the same time, with iterative product development and software, like you need to use Agile. And as we saw earlier with like Legacy and then Agile and Agile AI, you're starting to see Agile is really taking over the software development landscape. So key elements for success, you have integrated goals and objectives and success criteria. You're more adaptable to changing requirements throughout the project, and you have sustainability focused planning. So I propose a statement of work as being a friend in this regard, especially when there's like not really a proposal in place. And what a statement of work does is it aligns all these different groups, these stakeholders together to figure out what exactly the expectations are across the group. It establishes a clear scope, clear objectives that the team can follow, and it also reduces the uncertainty in the projects without, like I said, traditional grant funding. So I just took a screenshot of like one of the templates I shared with my team. Sometimes they prefer hands off, like they want to handle it themselves, or sometimes they want me to be a partner in that. And I'm not their manager. I'm more of like a business partner to help them with any administrative tasks or even structuring the project or just project intake in general. So really what a statement of work does is it outlines, flexibility for changes while still maintaining that accountability across the team. So I'm not going to cover all of this, but just here's an example of some of the areas that a statement of work might touch. It's just really, if you're able to look at this from the outset of your project, I think not necessarily planning everything in advance, but just thinking about it alongside the faculty, it makes it for a much more organized approach in your project delivery. So is a statement of work always needed for RSC work? No. A statement of work is primarily needed when there isn't like a structured proposal or it doesn't necessarily exist. This naturally aligns with Purdue's Research Software Engineering Center simply because we utilize a recharge rate where we use a recharge model to charge back faculty internally through internal transfer. So it aligns to our current operations. So when we use a statement of work, it's mainly when internal or self-funded projects where there isn't really a formal grant or proposal, or projects that have like very shifting or flexible requirements that need to be addressed. And like I said, when it isn't needed, maybe when there's a structured grant where things are already outlined and it's documented and the documentation is clear for all parties to understand, or if the project is part of some larger initiative that the agreements are already in place and it makes it much easier to follow. So like I said, we already have recharge-based engagements specifically for not to make money, but to recover operational expenses. And what you do is and if anybody has any questions about what a recharge center is, we could certainly talk about that. But you just take the direct and indirect costs of the team. So like your F&A, your salaries, and you determine a break-even rate, and then that's what you use to create a standard rate, and you could scale it up or down based off of hours or just time worked throughout the project, because a lot of RSC work is fractional in nature. So, and, when you come to a faculty member and they're like assuming that you're going to work 40 hours a week on the project, that is not the case. There's many things that RSCs touch all at once, and the transparency in that is demonstrated through a statement of work. So let's do a little bit of a case study. So let's say, university researchers, they want to, partner many different groups, NCAR and RCAC, my group specifically. They want to build an interactive wildfire risk modeling tool for Western US regions. So, chaos initially, like they come to us and they don't really know what they want. They're just like, we just know we want to do something with wildfire risk data. Okay, that's great. That doesn't help us very much. So what a statement of work does is it helps us guide those conversations to determine what the actual goal is and how this, tool is going to be built to support that visualization of the vulnerabilities across the regions in real-time model inputs. So, and another thing is scope of work. So can you also make this mobile? If I had the amount of times where a faculty member, like I said earlier, an RSE does a really good job and they're like, oh, that was awesome. Can you add this feature? Then I can go back and kind of shield an RSE and say, look, we didn't necessarily agree upon that. That's a good thought, but like maybe we should move that to a phase 2 and reserve it for future development. Like right now we're focusing on an MVP or something like that. So that's what really I found out when I joined the RSC Center at Purdue, is just there was a lot of scope creep and a lot of RSCs being taken advantage of. And I didn't like that too much as an admin. So I came in and tried to help that. So some objectives. So rather than focusing on deliverables, I have told my team that the best thing that we could do is focus on outcome-based goals. So when it comes to developing software, these outcome-based based goals are much more empowering to RSEs because you're not focused on like these rigid deliverables where they're like, oh, our group yesterday came up with a really good example between deliverables and objectives. Like you want to build a red house with a blue roof, but versus like an outcome-based approach where you're saying we want to build a structure that, you know, does X, Y, Z. It's much more empowering and it allows for the RSC to be much more creative in how they, you know, reach that end goal versus, you know, something that the faculty thinks they know what's best. And RSC can come in and say, well, did you think about this? Because this might actually be a better way to optimize what you're doing. So we focus on objectives rather than rigid deliverables. Another thing is timelines. So this is the area that I was talking about earlier where, you know, the fractional nature of work can be demonstrated. So, you know, you might have somebody working 20% FTE on this project or, you know, due to the fractional nature of our work, like the actual calendar duration might not be reflected in, you know, a 40-hour development project. So you could break it into smaller, more manageable chunks and you could tailor it based off of what the researcher is looking for or the research group. So some more categories here in the statement of work. So chaos could be, you know, we thought NCAR devs were doing this. And, you know, in the statement of work, it clearly clarifies and documents that, you know, the Purdue RSC Center provides a project manager and 2 developers. And, you know, NCAR provides the PI oversight and supports the climate model access. And all these external partners are kind of banded together to provide this feedback. Acceptance criteria is important across groups. Like I had mentioned, it's going to be different if you have, RSC projects are very much so interdisciplinary. So you're going to face different groups and different success criteria. So being able to have, you know, what defines success for all different groups is really beneficial to document from the outset. Risk management, sometimes it's hard to really identify, well, what could happen in the future. But as long as you start thinking about it and take a proactive approach, it's a lot better than being reactive, if you ask me. So just trying to anticipate risk and what that risk could look like and just talking about it from the very outset is important. Change management. So, you know, we see earlier, like, let's just add a 3D viewer at the end. Well, like that could be done, but I rely heavily on my RSCs to tell me if it's going, like how much time they think it could take. And I come in and say, yes, that's possible. Yes, it's not possible given the budget that we've been given. We do have a contingency as well. So in our projects, when we think that it's going to take, you know, 6 weeks of FTE to develop a certain software tool, we also include a buffer that's in adherence to the budget that's been provided to us. Communication plan. So nobody told us the mock-up changed. Well, the clarity is you're providing these weekly updates. And the best thing about a statement of work is you're able to tailor it. It's different. I just provide the template to my RSCs and I let them structure it however they want, or if they want me to structure it, I'm happy to do that. But it's really just a tool to get them to say, how does this faculty member want to communicate with us? How involved do they want to be? And that in itself is very empowering to the RSC because they're able to ask questions to these domain experts or these SMEs. So we involve SMEs as much as they'd like to be involved. And that helps us because the more we involve them, the more likely we don't accrue technical debt in developing something. So we also include closure criteria, cost and payment terms. So you see the statement of work can outline you know, a fixed project budget, but could it be monthly billing? It just depends on what specifically the faculty group is wanting. Intellectual property, like who's going to own the software tool. Sometimes we do a good job and we create a software tool and then the faculty member wants to commercialize it. And so it's like that gets confusing, right? So being able to document it from the very beginning is important. So the last thing is what we do at the very end of the statement of work is we all agree upon it. So if there's ever any revisions or changes that need to be made at the very beginning, we talk about those and then we formalize that commitment and we sign off. So before a statement of work, you might see like a lack of defined project roles. It's more ad hoc, it's confusing. There's frequent scope creep, there's inefficient time allocation. But with a statement of work, you're able to have more of a structured intake, standardized process that utilizes hybrid project management. And it also improves the documentation. And I can actually go to my leadership at Purdue and say, look at how much revenue that RSCs bring to our organization. We need more support, and here's how you can help us. That helps us at the state, local levels, and at the national level too. So being able to document this and provide actual metrics to performance to RSCs is what demonstrates their value locally and nationally. So the key outcomes would be reduced inefficiencies, better alignment, and across these interdisciplinary teams, and a little bit more scalability in the projects. So managing and reducing this technical debt is going to be really important with this statement of work. So you're just mentioning that, like, although we're providing structure, the way that we develop, like I said, is much more fractional in nature. So we don't want to develop inefficient code or outdated infrastructure. We don't want to be able to maintain, we don't want to maintain things. We're not there to debug, we're there to develop. And I think in a situation like where you're using a statement of work, what really helps with that is you're able to outline, you know, what projects, like what RSCs are working on what and how and what time is actually allocated. And you're able to be very transparent to faculty. And they actually really appreciate a standardized approach because we'll have repeat faculty members that come back and they're like, wow, like this is very streamlined. We already know what to expect. And I think that consistency is synonymous with quality. So I think it's really helped us scale our RSC center. So with structured management, it really helps us to, you know, have, you know, regular code reviews and quality assurance. It allows us to have adaptability and actually still utilize Agile in our development, but we can always go back to our roadmap, our SOW to say, hey, we didn't necessarily agree upon that initially. And I think that's really important. So what are the key takeaways and insights that I want everyone to think about is, you know, consider implementing hybrid project management for this, to balance this flexibility and the structure that's associated with your centers. You know, whether that's using a statement of work or just documenting things to align the expectations in the absence of traditional grant funding approaches. You want to be able to maintain this strong documentation, even on the non-technical side as an admin. And it also helps to reduce technical debt. So, and continuously. So if you're able to just do that, you're much more able to sustain the project. And so the final thought is this, you know, structure doesn't necessarily limit innovation, it enables it. And I think when my RSCs feel like they have a backbone and something that they could go back on and they have me as a shield, it allows them to be much more creative and have the freedom to be able to do what they love, which is coding and creating something that's new that could really change the society or the world. So I think that that's really cool and why I love working for RSCs. So I have a video here and I don't know if it's going to play it, but when I first started at Purdue, this was very different for me from manufacturing. And I was familiar with Agile, but she had told me that it's kind of like herding cats, but I don't know if it won't let me play it, but it's really a good video. It's funny. You guys will laugh, I promise, because it really is. There's so many different moving parts. And when you can get all those moving parts to work together seamlessly, it's something that the whole team can be really proud of. So thank you, everyone.
Thank you very much, Daniel. We have a feedback in Slido. So to read it through my laptop, give me just a few seconds. Yeah, as I said, this is a feedback from Spencer Smith. Great talk, Daniel. It resonates with my own experiences. I don't have a question, just a comment. Your combination of Agile and Waterfall reminds me of Dave Parnas's work on a rational design process, how and why to fake it. Thank you so much for sharing this, Spencer.
Yeah, thank you, Spencer.
And also having a lot of chaos with the videos in presentations reminds me, maybe we will revisit them to make them from your presentation.
Yeah, maybe so. Yeah, you have a question?
Yeah, thank you for the talk. This seems like a really helpful framework. And in my experience, a document like this is something that's easier to create when you have like a very defined scope for a project. Maybe it's like shorter term and like the things that you're going to implement are like really concrete. But I find that it's harder if a project is like on a longer time scale, or maybe it's like in the research realm and you're not exactly sure what you're going to be implementing. You kind of have to like figure it out after you dive in. So I was just wondering if you have any advice for creating a statement of work in that type of situation.
Yeah, that's a really good question. I think when I've experienced the projects that I've worked on, I think it is difficult to think upfront, like what could happen, what like in terms of risk or objectives. But I think it's a lot less chaotic than just going into the project with no documentation and then having a faculty member say, well, I wanted this and I wanted this, and where's that result? And I think that the best thing you could do for, you know, a longer term project where, you know, objectives maybe are ill-defined, that the faculty member or the research group doesn't necessarily know what they want to deliver. I think just having, you know, guided conversations and like I said from the outset, I think is going to help develop that statement of work to be agile in nature and allow for, you know, flexible and changing requirements. And I know that it's a document and it's like you have to go through like in predictive project management, you know, there's a change control process. Really with this, I just rely heavily on my RSCs to say, hey, Daniel, I think that this isn't really something we agreed upon. And then we just come together as a team and say, okay, well, if that's the case, then I'll be your shield to tell the faculty member that we can't do this and we'll find a different way. So I guess really learning as you go. I think documentation can only go so far, but I think really in the process of documenting and being transparent, you also create a very strong relationship with the faculty member or the research group where they feel like they can trust you. And I think that in a situation where there are changing requirements, let's say 6 months down the road, and your statement of work isn't really adhering to those changing requirements, then you have already built that trust to say, we document this and we're very professional and we want to figure out how we could do this based off of the initial agreement that we made. Hopefully that answers your question.
Yeah, that makes sense. Thank you.
Yeah, no problem.
Oh, we don't seem to have any virtual questions. Do we have anything in the room?
It actually,
Oh, okay. I don't think I can see the Zoom chat.
Oh, Phil. Yeah, I see Phil.
Oh, no, what I say is, do we have any questions?
can you
Oh,
see?
okay. Yeah, okay. Thank you.
Hey, Phil,
Oh,
go ahead.
Hey, thank you. So I'm actually the next presenter, and I think we are going to agree on a lot of things because we're tackling pretty much a similar problem. The question I have is really, I'm curious. So how, when you talk about in your facility and the research teams, so how large are those research teams? Like how many people working on the code and how many people like are the researchers? And are there any challenges related to that?
Sure. So good question. I think that the way that our system works when we have a recharge model and a standardized rate, it allows me to have flex in key personnel. So let's say a research project requires, a data scientist, a research software engineer, a sysadmin. I'm able to kind of pool all those people together with a standardized rate and determine, how they can work together on the project systematically. And I think that, when we're able to break the project down into more manageable chunks and kind of reduce those silos, that's exactly what RSEs wanted. And I'm glad that you had said you agree with me because this isn't my ideas. Like this all came from when I first joined Purdue. I just spent so much time individually with my RSEs to figure out what their pain points are. And they had mentioned scope creep and isolation and confusion on project outcomes. And so I'm glad that you agree because this isn't really my idea. It came from the collective intuition of my group. And I really think that I was telling my group yesterday, what does support look like for RSE? I really think it's going to evolve into multidisciplinary teams. They know that I'm a terrible coder. I can't write code. And that's why I have great people to work with like Chimdia over there who can really help me learn code, but I can help teach him, robust business practices. So I think learning from one another is really what's going to evolve RSE. And to your point, I think the best thing that you could do to, bring different groups in is to have this documentation to say your expertise is needed. And it's even easy for faculty to understand if there's a standardized rate, it allows for flex and key personnel. So that's what I include in the overall documentation, if that answers your question.
Oh, thank you. So yeah, I was really like the most curious thing I had was like typically in your in a research project, like what kind of a size are we talking about here, like for your
Oh,
research?
like a size of the research project itself or the team?
Yeah. The team.
So it varies in size. In some cases, like we have a project with the United States Air Force where we have to pull in different groups. Like I would say like 5 RSEs on a given project, spanning different disciplines. Or even sometimes if it's a larger initiative, we might bring in the whole, scientific solutions group, which, is composed with 10 people. So it just depends on if it's like a huge, large grant initiative or if it's a recharge initiative. A lot of the time it's just several people, like maybe 2 or 3 leads and any senior developer. That's really the scope of the team, I would say.
Thank you. I imagine that'll be pretty challenging to coordinate things like involving Air Force and so many people.
Oh, it is. That's why I had the herding cats. You guys need to watch that. It's really funny. I wish I could have played it. But yeah, thanks for your question, Phil. All right.
Okay, let's give Daniel another round of applause. And Phil, while we have you here, so don't go anywhere. So I am pleased to introduce Phil Dew, who is a current graduate student in computing and software at McMaster University. Phil, please take it away for your own presentation.
Hi, thank you. And thanks to Daniel. I think we're gonna, like I said, we're tackling very similar problems and we're gonna agree on a lot of things. And some of the approach that we're proposing here might be a little bit different, but on the grand scheme, we're really like we're on the same side of the problem. So my work, just in terms of the scope, we focused on small teams specifically. So nothing like so huge about like involving Air Force and like national labs and all that. So really, we're focusing on software development for maybe just a research team, like just a couple people, right? Maybe one or two domain expert, one or two developers, and that's about it. And frankly, we feel like there are fewer works on these because a lot of the works, a lot of study previously, and a lot of the sort of framework workflow that's more suited for larger teams. And so here's what we're gonna do. And this is sort of a overview of the presentation. And also, like Daniel, we would like to focus on the pain points of in various stages of the development. And just before we start, I want you to imagine two rows. That's also the works that have been defined in our studies. One is domain expert. Let's say I'm a researcher. I may be I'm a biologist, or I'm an environmental scientist, an engineer. I have my own research. I have, a lot of data I need to go through. I need to run some simulations, and I have a well-defined theories in my field. Or maybe there's something I cook myself that I want to try to implement in code. But frankly, I don't necessarily have the technical know-how to make that into a full-fledged software, hopefully open source software. And also above all else, my focus would be the research itself. I want to get paper out. I want to get academic recognitions. And then there's the developer who joins me into this joint adventure. Let's say you guys are the developer. You may be as a student who wants more experience under your belt. You may be someone also from a technical field, maybe even closer to mine, which is the reason why you joined my team. But you want to just experience something different, broaden your future a little bit. Or maybe you're even already in my team and you step up to be the developer. Now, what you want really is to have a long-lasting impact. Like as a developer, you want to have a long-lasting impact with your software. If not for benefiting of the whole academic community, well, for some sweet GitHub stars. And now we already see some misalignments in terms of knowledge. What you know and what you don't know. The developer may already know some good software development practices and tools, but they still need to learn a bit more about the domain knowledge to be able to successfully implement them. And there's also misalignment in terms of what is the priority for each person. And so our work is really to smooth things up and help with the collaboration between the two parties. And before we really started, now that we have like literature reviews and all that, but that's other people's experience. And for us, our very organic experience from our previous projects, one is a trajectory simulator that we had for like high precision spinning projectiles. And another one is more recent, with Syntheti, that is a turbulent flow generator. That this is actually this is actually a very typical domain expert developer cooperation we had, where we had people from the mechanical engineering side working on turbulent flow research, and then I was the developer to make all this, to both to empowering their research and also to act as sort of a software to generate like initial conditions and boundary condition for certain CFD application, like it's called direct numeric simulation and large eddy simulation, which is, if you don't know, it's very computationally intensive. So that if you can shave off some time in the beginning to jumpstart the simulation, that would be great. So it's just where this software is. And And so like on the right side, you see there's sort of there's like a, what's it called? Instance model that we have documented in our software. Really the key point, I'm not sure if you can see my mouse, is sort of this U value, which seems that's like the disturbance from a, like within the turbulent field at any given time and space, the disturbance from the mean velocity at that point, which looks not so complicated as a equation itself. But imagine if you have to do this across millions of eddies and billions of points and in continuous time, that's the main problem that we're running into. And jumping off point for my work is both previous Dr. David Parnas, who like back in the 70s pioneered a lot of the software requirements and modular design work. And then also my supervisor, Dr. Smith, he had a document-driven template he has been using for his research and his students. Now, these are great. These kind of documentation-driven process are great because they're kind of in line with the academic expectations of research. Research is all about being replicable and other people being able to jump to build upon your work in the future. Well, if your research is powered by some sort of software and then other people have no way of running your software, then what's the whole point, right? But frankly, we don't see a lot of, we see pretty slow adaptation for adoption for these kind of framework. I think maybe Daniel, like previous friends, will also agree that sometimes people just don't want to have anything to do with this. They just want to have the development work and not having to worry about all these because, well, first of all, there's overhead. You're essentially asking people to do more things. And also the evolving research is another problem that, like Daniel said, if I'm a domain expert in the beginning of the research, I don't really know what I'm going to do next at all. Like my mind's in jumble. How am I supposed to tell you, the developer, what exactly to do? So this is where we come in. We try to smooth things up. And our work here is the more tangible form of our work is a GitHub template that you can just adapt and use yourself. It has all the good bells and whistles for being a development template. It builds your document website. It has there's cross-linking, good with citations, and there's very easy. So for me, if I'm a domain expert, I'll really appreciate that I'll be able to easily create issues specifically linked to a certain part of the documents and edit the page. And everything is in bite size. So you're not throwing entire like giant PDF documents at me. Everything is well manageable. And so the first thing in the process that we introduced is this what's called information gathering meeting process. Essentially, this is what I said, how to help the developer extract the correct information from my mind to build the software. And it goes in the form like a technical meeting, like typically an hour, but depends on the complexity of the problem. It can be longer. Or you can schedule multiple sessions. Essentially, how it works is that the developer would guide the domain expert through a series of very specific questions that we've designed to help them extract correct information in different areas. And as you can see on the right, we actually took sort of a like not waterfall, but like a V model. There's a reason for it. We'll talk about it later. That the information gathered here is going to feed into different parts of the document and development process. Now, the reason why we took a V model is because we want to have a separation between high domain expert involvement phase and low domain expert involvement phase, which essentially the domain expert, they want to do research. You don't want to take up too much of their time when you're essentially just writing code. Now, what are these questions? So this is one of the examples. So it's about the scale of the problem. Now, we had this question specifically because the problems that we have ran into when we were developing Syntheti, well, everything was well documented. The theories was well understood. But the initial design we had was very beautiful, is well encapsulated as a tech demo, and it really mimicked the physical system. But like we didn't really like, we never had a discussion in terms of what's the typical use case. And when the actual use case is getting thrown in, it quickly fell apart because it's way too computation intensive. It took up way too much resources to be practical. So if we had this discussion in the beginning, that will help us really steer clear of this problem and really think about, like, pre-think about a design, what kind of design you're gonna have, so you don't run into problems like this. And this is sort of a traceability matrix of what different questions will map to different parts of the documents. And after that, you're gonna build your documents, like you document your theoretical models, your input values, and we actually have some suggestions in terms of very specifically, what kind of input you should have. Really, the idea is that because the domain expert, like the researcher in your group, is going to use your software in a more exploratory way, you really want to be able to enable them to to tweak your software to work in different ways. You have as many input as possible to make your software work in different modes. And then later, let's say other users, they want to build upon your research, they come in and they just took your software as it is. Then in that case, you're gonna provide default values for them to sort of start with a typical use case. And another idea that we had was really to cut down some of the documents in terms of design. Now, if I'm a domain expert that I'm not really familiar with code, I'm not really good at it, I don't really need to read your detailed design documents, and so there's really no reason for you to create such a beautiful formal document for me. Well, you should be just writing your code. So the idea is that you should really use the bells and whistles of modern IDEs and programming languages to essentially, during your design, build the code skeleton, if I may say so. And reasons being, like, first, I'm not gonna read that, and second, if you're gonna change anything, it's human nature to jump into the code, and then now you run the risk of code diverging from your document. So why not just put them together? And also, that's what is becoming increasingly relevant these days, is that if you use any sort of AI coding assistant tool, then if you already have everything well documented in the code, it really helps the assistant to get context and help them generate code. Not to say that you should just take it for what it is, but it's a good starting point. And another aspect, and that's we think is pretty interesting, is how to properly advertise your software. Now, if I'm a domain expert, the problem is that I'm not that motivated in helping you as a developer writing good, sustainable software, because I feel like I'm not getting, for my effort of doing that, I'm not getting enough recognition. The recognition I get is from my citations. It's pretty realistic. It's from the citation I get, the conference I go to. Now, and so how do you motivate me? Well, a way to do that one, there's just several ways. One way we found out is that, well, you can properly advertise your software. So what we learned from some other project, we've seen, like, this is one of the machine learning project, is that they kind of squish the software and the paper into sort of a one unified entity, that if you use the software, you're gonna know about the paper. If you read about the paper, you're gonna know about software. So they can't really exist without each other. So that's one way to give the software more publicity. And another way is, as you have potential future users who want to adapt your software, aside from your typical very detailed user manual, what you really want is a quick start guide. This is what we learned from, like, self-hosting community, where people would have like Docker containers or prepackaged binaries where you can let the user spin up a typical use case within like 5 minutes. Well, obviously, this is only relevant if your software is runnable on a personal computer. If it's by design to only be able to run on clusters and supercomputers, obviously this doesn't apply. So in this way, it helps with user retention. If you have more potential users coming in, use your software and giving you feedback, now there comes the recognition. Future look about this. Well, first of all, we do recognize it is perhaps a little bit hard to market this towards individual project teams, individual researchers, because essentially you're still asking them to do more work. Despite how much we cut down the overhead, there's still a bit more work. Now, it will make more sense in terms of on an organization level, like what Daniel said, is if you have a department or your facility would adopt something like this or similar to this, then as students come and go, when they're done with their research, they leave, and another grad student come in. The previous work is not gone to waste. So make more sense there. And in terms of future work, other than an experiment to really validate our process, which we do have a design for it, we just didn't have time for it. Another direction I want to look to is even smaller team. Let's say, what if the domain expert, the researcher itself, him or herself is the developer? Because, well, nowadays it's easier and easier to get software development work done with all the tools you have. So what would be a better process for them to develop sustainable software to have a long-lasting impact? And this is all I have to say. Thank you for your time, and I'm open to questions and comments.
Thank you very much, Phil. We don't seem to have any questions in Slido, but we have one at least in the room.
Yeah, I'm gonna pull an Uno reverse. Great talk. One of my questions, and I really like your approach and how you do the information gathering up front. I love that. I think that really helps with structuring the project. My question for you is you had mentioned, so much of RSE value and recognition is in these citations and these publications, but RSE has so much more to offer than just that. And I'm just curious, within your group, have you faced any roadblocks specifically for conveying the value of RSE within your organization? And if so, what might those roadblocks be?
Conveying the RS. Well, I was the developer myself. It's the other person is the other person, and his teams behind him is the domain expert. Well, so I mean, is your question specifically towards like the developer side of the thing, or the researcher
Just
side?
research software engineering in general, like
In
outside
general.
of just being a developer, whether you're managing the project or you're developing it. I think my question is just pertaining to, RSEs traditionally, like whether they're involved with citations or publications, that means that they're a strong RSE. But I think that there's so many other areas that RSEs can contribute to research and their organizations. And I'm just asking, like at McMaster, like how do you guys convey your value to the broader organization outside of just being in citations or publications, if that makes sense?
Okay, so really what we really want to focus here is that yes, they want their citations. So what we really want is to have this thing that to have it to be something that you can keep, essentially, to not like I said, for it to go to waste. That because really the biggest problem that not necessarily we run into within the process, the project itself, is that when we look at other things, that other projects that potentially we can adapt, or some works that's done previously, we frequently run into problem that yes, they have everything there, they have the repo and everything, but it's just like, how do I actually use your stuff, right? I know you probably had great work, but I feel sorry but I just can't use it. So we want to avoid is for future people to run into problems that we run into, essentially.
Yeah, thank you.
Yeah, thank you.
Thank you. And we have one more question from Kate Rasmussen. Great talk. Have you heard of the Journal of Open Source Software? If so, do you think publishing in this journal is a way to help motivate both domain experts and developers to get their work recognized? And I would like to follow up on this as well. It would also help with, in addition to advertising your software, this would help with getting more citations as well. So I'm curious about your thoughts.
Oh yes, so we actually did publish our work to Journal of Open Source Software. It's still in the process. I was actually pleasantly surprised that something like this exists for the software to get some recognition, because this journal is really it's mainly focused on the software that empowers the research. Like specifically when you write the paper about it, like it's a short paper, but they specifically ask you to not talk about the research, but talk about how your software empowers the research. So this is really things like this is really a good way for you to get recognition. Especially this is more in line with the traditional academic thinking that you're getting publication and citations, other than because as developers, a lot of time you understand that it's not necessarily the citations you get, but often it's the GitHub stars that really shows that you are the guy. But a lot of the time, it's hard to convey this idea to more traditional researchers, where they probably didn't even know what GitHub is. Thank you.
Yeah, we have one more question, and I'm sure we can cover that as well. And let this one be the last question for Phil. So great talk. Have you published this as a guide for developing small RSE projects somewhere? Would you love to share it with some people?
Okay, great. Other than the proceeding of this conference, this is my thesis, and I just completed my defense. So you will see that real soon.
Congratulations on that one as well.
Thank you.
And let's give him. That said, we can move on to our next speaker, which is going to wrap up this session for us. So bear with me while I find my notes. Dr. Maria Patrou, thank you so much for coming here. And Dr. Maria Patrou works as a research software engineer at the Oak Ridge National Lab. Dr. Patrou, please take it away.
Hello. Can you see everything and can you hear me?
Yeah, we can see everything and we can hear you very well. Thank you.
Awesome. Thank you very much. So in this talk, I'm going to go through the modernization process that we followed in order to bring more up-to-date specific tools in spectroscopy. This work took place in Oak Ridge National Laboratory at Spallation Neutron Source with myself, CliMA, and Andres Savitsi. And I just want to give a brief introduction to these tools, the motivation behind it, the steps that we took, and how standard processes can become part of standards, and then the lessons that we learned during this process. So we're looking at the tools in the realm of material science and neutron scattering, in this case, in the experiments, we have a beam of neutrons that hits a material and then it's scattered, and the information about these neutrons collected by detector panels, something like cameras. Think of it. So there are various techniques that they study this neutron properties. In spectroscopy, the focus is on interaction between the atoms of the material by looking into the change in speed and direction of neutrons. So there are several tools, and especially here that we develop and maintain. But after we have this heavy development of a new tool, then the tool reaches at a stable state, and then maybe no changes will occur for a big duration of time. However, there is a time that there is a need for modern libraries, and these libraries they are dependencies for these neutron scattering tools. And what we notice is that for recent versions, the functionality that they depend upon might be deprecated, so there might not be backwards compatibility. So at this stage, it triggers an investigation on the package dependencies, looking into the building, and also looking into certain code updates and optimization. However, when we modernize the tools, there are some prerequisites that they need to be in place, and then we can do the actual upgrades with the goal to have the same procedures that we already use for existing projects. So basically, we're going to go through the steps that we followed for two tools, Multiphoton and Histogram. Both of them are open source. They're provided by GitHub. They're Python conda packages. Multiphoton converges powder spectra measure the direct geometry in elastic neutral spectrometers to photon density of states, while histogram essentially provides a data structure for creating histograms, so visual for the histogram plot, and taking slices of them and also performing numerical operations. The important part is that histogram is used in multiphoton. So in order to modernize these packets, we had to take some steps. And what we did is first having an environment, then be able to install and package the tools, having a testing suite, code static analysis and some optimizations, have CI/CD process in place, on documentation with read the docs, and then do the package upgrades. So to begin with, we wanted an environment. We chose a conda environment in order to have these isolated and as consistent as possible installations. And inside the environment, we could set up the dependencies that the tools depend on by looking into several parts of the code, and also include dependencies for processes like installing it, release and deployment, doing the testing, and also including a static code analysis tool. The second step is that now we have the environment, and now we want to be able to install within that environment the packages. And we want to be able to have them first as a Python package in an editable mode, mostly for developers, and second as a conda package in order to be able to package it and publish it to Anaconda whenever we are ready for release for the users to be able to install it easily. And also you have modern Anaconda builders. The third component is that now that we have this installation in place, we want to be able to introduce a testing suite. It already had tests, but having something like PyTest, which later we're going to use it as part of our CI/CD process. And in this stage, we fixed any failed test. We put all artifacts that they were produced during this testing phase in temporary files to ensure that there's no clutter in the source code. And then we also marked the test when they use specific third-party libraries that we care about, and also whenever they have temporary file creations. And also we included the code coverage, so to have reports and threshold for future pull requests to ensure some code quality. So the fourth step, another important step, was to introduce static code analysis tools. And these tools, when we follow, they ensure best software practices. They also help us to focus on the code. By giving us this information about different parts of the code, like import order spaces, it helps drive the improvements for current states, and also whether we want to make some of these improvements on the code in the near future. Also, it helps to clean up the code, to make it more unified, and also to be more focused on specific code components, as well as looking at the whole picture. We also included as a pre-commit configuration hooks to also ensure future code contributors abide by these practices. The fifth step was to introduce GitHub actions for pull requests in the main branches that we have. So during this step, we wanted to be able to create Python packages, to execute the testing suite, to produce code coverage report, to be able to also build Python and conda packets, and then publish to Anaconda when we want to have a new release. The sixth step was the documentation. So there was already some documentation, but we wanted also to release it through read the docs. It's something that we already use with other projects. And we also wanted to document the previous processes. So the installation steps that we use in order to build from the source, to install actually from the source, they were included in README. And then we connected in the docs, the user documentation. Now, at this point, it was also very important to share with the developers the information that we gathered and we collected with this process and presented in a clear manner in order to be able to have in the future more efficient code contribution. And this ability of sharing information and also documentation, I think it was one of the most important steps. Now, the last step was, at least in this process, was to do the package dependency upgrade. So at this point, we want to eliminate any dependencies to outdated packages. And in order to achieve that, we followed essentially one of the following methods. Either moved, we pinned pretty much to a latest dependency package, for example, the Python version. Another case was to pretty much replace a specific package with another one. So use Python logger mechanism over journal, or in the third case will be to replicate the functionality and remove the package as a required dependency in the source code. Now this method, it was chosen on a case-by-case basis. Depending what we had to do, we had to follow one of these. Now, the next step is the software architecture. When we're visiting this code, sometimes we want to see whether we can apply certain improvements on the software architecture. And in my group, we use model view presenter architectural pattern where we have this front-end and back-end code. Now, it doesn't mean that it's applicable for every software code. And at this point, I think it is important to understand how the technical code works, the technical functionality, and maybe make some incremental changes if they're feasible. We did face certain challenges through these steps. We had to put some temporary solutions in place until there were certain upgrades that were possible. We introduced a new way of installing the software through this conda packets in Python. It used a little bit of the previous one, and it certainly had some pros. But the biggest problem that we faced was the lack of documentation on the technical part of the code, such as installation and release, and the different functionality, the different parts of the software code. We spent time on understanding the architecture and the functionality, and also, I think it's another important thing is that we have to ensure that the changes that we make, they complement the software rather than creating new patches. Because that will help if we have complemented changes, then it will help for future code to be efficient. Also, we noticed that in our tools that for spectroscopy, we have some characteristics in common. And that is that we have tools that they are mostly desktop tools written in Python and PyQt. As conda packages, they follow CI/CD with GitHub Actions. We have static code analysis. Whenever possible, we use this MVP architectural pattern, and then we provide technical documentation for developers and users published through the written docs. And what is notable is that since there are all these technical features in place, they kind of become requirements of any future software in spectroscopy. And as we saw, lack of these features like this technical documentation can create challenges in order to have product contributions in a timely manner efficiently. So from the lessons learned of modernization, we can be advocates on delivering changes that endure over time. So providing technical documentation that is really on par on the code base, and also include future directions and current limitations of the software. It's something that we include on publications, but I think it will be also beneficial to have it on software. And also aim at changes that enhance and enhance the current software code rather than doing these patches. So in conclusion, the process of reviving this legacy code proved that we had to have some processes in place before we actually do the upgrade. And since this place they need to be there, then they can serve as standards for software applications. And that will help current and future research software engineers decrease the time spent on understanding the software. And some of these key technical fixes that we present that for project maturity and progression, I think it is technical documentation which provide information about the code, about limitations, maybe even future work, and the CI/CD with a comprehensive test suite in order to ensure future contributions do not break the current software. Thank you very much.
Thank you very much. Any chance? Do we have any in-room question? I can have one. So you went through the modernization of the legacy code way for your case, and there is a lot of discussions of RSEs around should we sunset and when should we sunset our legacy tools as well. And this might be a case-by-case study for sure, but from your own perspective, if there is any, can you hear me?
Yes,
Yeah,
yes. So
if there is any like red line between should we sunset a tool and when should that happen, or rather than that, should we modernize a tool from your own perspective?
yes, I think it's definitely a case-by-case scenario. We definitely see that some things they take a lot of effort to be modernized, some other things they don't take as much effort. So it has to do a lot, I think, with how much effort we are willing to make for a tool to be modernized. And I would say, yeah, there has to be a case that we should draw the line and say maybe we should start over, maybe it will be more efficient. Maybe the things that they are done in the past in a certain way now they can be already are solved in a more efficient way. Maybe we can use that way. But I certainly don't have an answer for every case. I mean, in our case, it was worth it to do the modernization, but I can see where in other scenarios it might not have worth the effort.
Yeah, thank you. Thank you very much. Any more questions? We have one from the room. Ryan, go ahead.
Yeah, thanks for the talk. I feel like there were a lot of echoes to the talk I gave on Monday. So it was nice to see a lot of the same work. I guess one thing I think about, and I feel like a lot of the automation that's set up helps with this, but like I think about the piece of code that I modernized, and that was like I wanted to modernize it, and I did, and now that's done. But like I want to keep it modern moving forward, and not just have this be like a burst and then do it again in 5 years. So, what are your thoughts on keeping the code modern, especially if it kind of sees activity from time to time but isn't constantly used?
Yes, so I think we will have to go back to it from time to time, and depending how it's done, some people or there is some preference on pinning the dependency versions, and that makes it sure that whenever you run your tool, you know exactly the version and the dependencies, and that it's important for when you're running, let's say, experiments to know exactly what happened. So the next time you're going to run it, it's going to be with the same requirements. But since we pin these versions, just as an example, that means that when a new version comes in, we don't know whether it's compatible or not. And if we wait 5 years now, it's going to be so many versions ahead. So I would think that periodically we will have to go back and just do this exercise. Let's push it to the latest version and see how or if we need to make any change. And then that's how we have this incremental progress of our code instead of just wait 5 years and then have to deal with 5 years of progression all at once.
Yeah, thanks. I feel like it's sort of a discussion to have with like the end users as well, is to like let you know what sort of sustainable support is this for the is there for this work. So thanks.
Thank you. Any more questions for Maria? Going once, twice. Okay, wrapping up the questions for Maria. Maria, thank you so much. Please join me in thanking Maria again. That said, we are wrapping up this session, but I have some reminders. First, today's lunchtime is longer than what we did in the last 3 days, so we are coming back from lunch at 1:20. That's one thing, and because we have some longer time there, we can still take some time on some of the things to cover. First, we had some questions on Carol's presentation, and I wasn't able to catch them before I transitioned to the next speaker. Carol, would you like to answer them now? If you would like, you can, yeah, take on that mic. The first question, I'm not sure if it is, yeah, it seems readable, right?
I can read it, yeah.
Okay.
Question from Eric, really exciting and good work here. I really love to see things like this that bring in better practices and better code. Thanks so much for sharing. Appreciate it, Eric. Yeah. From Amit, was there any single good aspect of Perl that you miss in Python? I mean, if I'm being completely honest, I still feel like I really don't know Perl, and I was just copying scripts and hoping that they worked. So I don't really, yeah, I would say no.
Thank you, Carol. Thanks for the questions. Daniel, we were very excited about your video, and I think we can pull that up to screen. Okay. Okay.
This man
Go
right
ahead.
here
Yeah.
is my great grandfather. He's the first cat herder in our family. Herding cats. Don't let anybody tell you it's easy. Anybody can herd cattle. Holding together 10,000 half wild short hairs, well, that's another thing altogether. Being a cat herder is probably about the toughest thing I think I've ever done.
I got this one this morning right here. And if you look at his face, it's just ripped to shreds, you know?
You see the movies, you hear the stories. I'm living a dream. Not everyone can do what we do.
I wouldn't do nothing else.
It ain't an easy job, but when you bring a herd into town and you ain't lost a one of them, ain't a feeling like it in the world.
UDS, managing the complexities of the digital economy.
Next, thank you, everyone. Thank you, everyone. I think we can head to the lunch now.
The- like, you know, yeah, it's like a, you can expect like maybe per second, yeah, like a large amount of this. Oh, actually, no, yeah. Yeah, I cannot people. Okay. Let it go through. Yeah, I think it's. Some CSM like one archive.
we have a couple more minutes before we get ahead and get started. But before we do get started, I do want to call out the administrative team, the multimedia team, and also the catering team for the amazing job they've done. It's gone seamless because of all of their efforts. You should see the chat. They have everything coordinated. They're talking to each other. They've done an amazing job. And I just wanted to call out and thank them for everything. So thank you. And it looks like everybody's kind of settled in. So we'll go ahead and get started a minute early if that's okay. So first off, we have Julia Sloan, and Julia is a research software engineer working on the Climate Model Alliance group at Caltech, the CliMA group, and she's going to be talking about leveraging modern computing and calibration-driven development for climate modeling. Thank you.
Okay, how about now? There we go. Hello, everyone. My name is Julia, and today I'm going to be talking to you about the project I'm working on, which is called CliMA. It's a climate modeling project, and this talk is kind of going to focus on two components of it. I'm going to talk about how we use modern computing to enhance the project, and I'm also going to talk about our integrated calibration pipeline and how that kind of drives our development. So before I get into those topics, a little bit of background about the project first. So we're building a new Earth system model in Julia. And this project, CliMA, it stands for the Climate Modeling Alliance, and it's a combination of efforts between Caltech and MIT. So here you can see a picture of some of the people that have worked on this project, not everyone. And I want to really acknowledge that this is the work of many, many people and not just myself. So the efforts of not just these people, but also people not pictured here, their hard work has also gone into this. And maybe I'll just note also that this team is made up mostly of research scientists and software engineers. And something that's maybe a little bit unique about our group is that the research software engineers that are working on this project are working like only on this project. So we devote all of our time to working on this model. So here we have a beautiful, very picturesque image. And you may be wondering, we're at a software engineering conference, why are we looking at a picture of the beach? And while this may look like, to a normal person, to a layman, this is just a very picturesque image, to a climate modeler, they're going to see all of the complex physical processes that are going on in an image like this. So in the atmosphere, you have stuff like atmospheric circulation and radiation. You have things in the land like photosynthesis and runoff. And of course, we have the ocean where we're keeping track of ocean circulation, salinity, dissolved CO2, and of course, much more. So for those of you that may not be as familiar with climate modeling, this is just to give you an idea of the many, many physical processes that are represented in a model like this. And hopefully knowing that there are so many physical processes going on, this gives you an idea of why a model like this is very computationally expensive. So for example, a global climate model like this is typically run on a timescale of decades to even centuries. So when we're targeting a long run like that, state-of-the-art Earth system models will typically run on thousands to tens of thousands of CPU cores for weeks to months to produce these very long timescale, relatively high-resolution simulations. And of course, the computational requirements will depend on the temporal and the spatial resolution, but this is just to give you kind of an idea of why performance is so important in this setting. And a shout out to Derecho, which is one of the clusters that we use for testing and running our model. And one of the research scientists in my group, when she came to visit, sent me over this nice picture to include. So now I'm going to get into kind of the first topic that I want to mention in this talk, which is modern computing and CliMA and how we use it to our advantage. So the first thing here is we're developing our model in Julia, which has been kind of like a hot topic this week. And I just wanted to highlight some of the benefits that this affords us. So the first is that writing our code in Julia allows us to have largely hardware agnostic software. So of course, we have work done under the hood to kind of hide some of the internals of running on CPU versus GPU. But in the actual run script, when you set up and you run the simulation, if you want to run on CPU versus GPU, you just change one environment variable. It's just a one-line change. So this is something that we find is very helpful for users and kind of improves their experience using the model. And something else that we have found very useful, especially as it relates to this project, is that writing in Julia allows us to both prototype and improve the performance in one language. So because this project involves both scientists and software engineers, we want to be able to cater to everyone's needs. So we want the scientists to be able to test out new hypotheses, new parameterizations that they're interested in. But we also want the software engineers to be able to dig into the internals and really write performant code. So writing in Julia allows us to be able to kind of like meet both of those needs with just one language. And the next aspect of modern computing that I'm going to touch on is that CliMA is an entirely open source project. So there are a couple of benefits to developing our project like this. We found that it facilitates user interaction and scientific collaboration. So even though our model is still under development, we've had some like PhD students from different universities around the world that are interested in using the model and like getting involved with it. Having our model be open source also promotes transparency and reproducibility, which are very helpful for having open science and making sure that other scientists can recreate our results in the future if they're interested. So with that, I'm going to transition now to the second part of the talk, which is about the calibration-driven development of the CliMA model. And I put this image here, and it kind of has a lot going on, but the general idea is that in the middle here, we have our Earth system model with all of the components that it contains and all of the physics that it contains. And at the top here, we have these satellites, which are taking observations of the Earth and producing this observational wealth of data that we have access to. And one of the goals of our project is to take all of that data and assimilate it into the model to help improve our model. So I'm going to get into a little bit of kind of what that process looks like for us. So to motivate why we want to use this data and why it's actually important in our case, I'm going to introduce this idea of free parameters. So Earth system models sometimes use equations which rely on free parameters. And what I mean by this is parameters that don't have well-defined values. So here at the bottom, I have a table showing some of the parameters that are involved in our snow model. And this is maybe getting a little bit into the weeds of the science, but if we just focus on this, this second row, which is the albedo of snow, this is a measure of like the reflectiveness of the snow. This is something where we know albedo is like a fractional number, so we know it's going to be defined in the range 0 to 1. It's going to be somewhere in there, but we're using one value of albedo for all of the snow over the world. And if you just think about it, and maybe you've seen snow living here in Boulder, when snow first falls, it's really bright and white. And so it's going to have a higher albedo. Whereas as time goes on, the snow is kind of sitting there, maybe it gets dirty, and the albedo of the snow is going to change. So one of the challenges that we face in our model is we don't want to have so many of these free parameters. So we kind of make the trade-off that, okay, all snow is just going to have one reflectivity. But you can imagine this is very poorly constrained, and it's hard to choose a value for what that should be. So the way that this typically works is model developers will read through the literature, look at what other models do, and kind of choose like a reasonable value to use. But of course, maybe the literature is not using the ideal value. We don't know really like how the other model developers came up with the values that they're using. So there's this idea of calibration that comes into play where we're trying to really nail down what value these free parameters should have. And so there are some existing methods for doing this calibration with existing models, but we've found that they're pretty time consuming and not very scalable for large numbers of parameters. So one option is hand tuning by scientists. So a scientist will choose one value for a parameter, run the model with that value, and then compare the model output to data and see kind of how it performs. And from there choose to make the parameter larger or smaller, or if the results are good enough to keep it as it is. As you can imagine, this is very labor intensive. It requires a scientist with a lot of domain knowledge running a model over and over. So it's very time consuming, and we wanted to have something a little more automated. So another option, which is kind of described at the bottom of this slide, is grid searching or random searching. So if we look at this image in the bottom right, we have two parameters, x1 and x2. And there's a contour plot here, which is like a loss function. So comparing some function of these two parameters to data. And we want to minimize this loss function. So we want to choose parameters that are going to give us the smallest deviation from the data. So let's say that the red is the smaller value. So we want to choose values of x1 and x2 that are going to get us closest to this kind of like red circle that you see on the left side of this plot. So that being said, if we do grid searching, what we would do is run the model over and over and over again for all of the combinations of x1 and x2 that are shown by the x's on this plot. And for each of these model runs, we compare the output to the data, we evaluate the loss function, and we decide which parameters we want to use. So as you can see, even from this small example with only 2 parameters, this really adds up to a lot of model runs and becomes really computationally expensive. And it's also slow for larger numbers of parameters. So what some members of my group have done is develop a new ensemble-based method for calibrating models. So the way that this works, I won't get into the details a little bit too much because it's not that long of a talk. But basically, we start out with a distribution for each of the parameters. We sample from that distribution and set up an ensemble of model runs using those parameters that we've selected. Then for each of those model runs, we evaluate our loss function by comparing to data. And then we create a new distribution for each of the parameters that's centered closer to the values that gave us a smaller loss function. So we kind of follow this iterative process where we're getting closer and closer and converging to parameter values that minimize the loss function. And I should say maybe that there's this idea of uncertainty quantification as well in the modeling community that I'm not going to go into here, but my colleagues have also developed a kind of machine learning emulator-based method for uncertainty quantification, which also significantly speeds up that process, which is kind of related to the calibration. And in addition to being less computationally intensive, our calibration pipeline also uses a file-based interface. So because it's just using text files to interface with the model, it's actually agnostic to whatever language that the model is written in. So our model happens to be written in Julia, but if another climate model is written in Fortran or C or something else, this same pipeline could be applied to that model as long as they can take in these parameters from a text file. And so the message that I really want to deliver here is that by having this performant calibration approach and uncertainty quantification approach as well, we're able to include the calibration process within the development process. So what I mean by this is as we're developing our model, we're able to improve the model, get it to a place where we're pretty happy with how the physics looks, and then run our calibration on it and improve the parameters and evaluate the accuracy and see how our model is doing and decide at that point if we need to make further improvements to the physics, if maybe there's some area that we're making too many assumptions, or maybe now that we've calibrated our parameters, our results are good enough and the physics is complete enough that we can say that a part of the model is sufficient. So I just wanted to give you a quick example of some preliminary calibration that we did in the past. So this is looking at our land model. And the value that we're looking at here is solar-induced fluorescence. It's not important what that is, but basically it's a measure of photosynthesis. So a brighter color here, like a more yellow color, is an area where we have more photosynthetic activity. And an area where we have darker colors means we have less photosynthetic activity. So right now we're looking at our model output before we calibrated anything. So you can see that kind of broadly we're getting a pattern that you might expect. So in areas like the Amazon rainforest or like sub-Saharan Africa, we have more photosynthesis going on, and in more deserty areas, there's less. But if we look at observational data of this quantity measured by satellites, we can see that while we're getting the kind of general trend right, we're really missing like the amplitude of this signal, and we're underpredicting photosynthesis in a lot of those areas that I just mentioned should have high photosynthesis. So after calibration, our model results look more like this. So you can see it's still not perfect. It doesn't match the observational data perfectly, but we've increased the amplitude a little bit so we get kind of more photosynthetic activity in those like tropical areas. So these are just kind of some preliminary results to give you an idea of what applying the calibration pipeline might look like. So we've since improved our photosynthesis model and made other changes. So this is a little bit outdated, but yeah, I wanted to also mention that here, this is an example of applying our calibration to just the photosynthesis model, which is like a subcomponent of our land model. But this can be applied to like the land model itself. This can be applied to the coupled model. So it's really nice that we have this calibration pipeline that can be applied like at any level in that way. So with that, I'd like to thank you for your time, and I'll take any questions you have.
Thanks, Julia. Any questions?
Thanks, Julia. Great talk. This might be a naive question for someone that doesn't necessarily work in the model space, but what is usually the practice for writing those parameter files if they're not text files? Are they usually then written in the programming languages and kind of native to the programming language?
Yeah, that's a good question. I can't say that I know the answer to it. The work that I'm presenting on here is not really stuff that I work on directly, so I'm not sure. I would imagine maybe sometimes the parameters are, like you said, like they're just specified in the programming language of the model itself, or maybe other models can also take in like config files that specify parameters, but I'm not completely sure.
Yeah, well, your approach seems to be very useful in the way that you described how it could be used with any kind of programming language in any model. So
Yeah,
appreciate it. Thanks.
thank you.
More questions?
I have a question. Thank you for your talk. It was great. I have a question if you have any methods to ensure or maybe deal with some not optimal minimalization, but some local minima that you can find by selecting some parameters, starting parameters.
Yeah. So yeah, this is kind of a common problem when trying to calibrate climate models, because typically you might want to use like a derivative-based method, but because the data that we're comparing to is really noisy, you have a lot of like local minima that aren't necessarily the global minima. And we found that using this ensemble-based method, because it's derivative-free, it's not using any derivatives, you actually kind of like not lose, but you sort of like overlook that local information, and you get more of like a global view of the data. So we found that it does a good job of finding the global minimum in that way.
Okay, so you're running this several times and then iterate every time?
Yeah, exactly. So typically when we're calibrating the model, we'll run with like maybe 3 or 4 iterations, something like that. And each iteration contains an ensemble of maybe like 10 model runs, something like that.
Okay, thank you.
Maybe one more question on a similar vein, because I didn't get it. Do you try to calibrate one or few parameters at one time, or all of them? Because I'm interested whether they are independent enough. And for example, trying to calibrate one parameter, are you encountering issues that they are maybe compensating for some other ones, whether there is independence that can be either measured or ascertained by researchers?
Yeah, definitely. I think introducing compensating errors is something that you definitely have to be aware of and be kind of like mindful of when you choose which parameters you calibrate at the same time. So depending on like which part of the model you're calibrating and which parameters are involved, you kind of have to like choose on a case by case basis which ones you're going to calibrate like at the same time.
And since we have a couple extra minutes, I'm going to ask a question as well. So in the beginning of your talk, you mentioned, that CliMA is a community model. So are there any particular steps the project has taken to make it easier for the community to contribute to the code?
Yeah, I think I guess I should say that right now most of our contributors are within the group itself, but we're very focused on having users from outside of the group. So I think to that end, we really emphasize like having a clean user interface and designing all of our simulations and our models with the users in mind. So making sure that while maybe they the inner part of the model, it has all this physics built in and it's very complex. We try not to let that shine through to like when the user is setting up a simulation and doing it in that way. So I think like kind of separating the complexity and having like modularity in that way helps.
Thank you. Any more questions for Julia? Let's thank Julia one more time.
Thank you.
So next up, we have Eric Kluzek. He's a software engineer at NCAR working within the land modeling group of CSM. Sorry, he's going to be talking about helping scientists embrace their inner research software engineering.
Great. Thanks, Sherry. So this slide is much too busy, but the most important thing I want to highlight is my team. Whoops, I need to go backwards. Okay, my team, I'm really proud to be part of a great team that's wonderful to work with, and it's been a great experience for me. So, but this is much less busy. We're going to talk about embracing your inner research software engineer, and it's something that we need everybody to do. But I'm going to start with a little story. Has anybody had an idea that you were excited about get crushed really quickly? I think everybody has, right? So this is kind of a 20-year story about that, because 20 years ago, I was really excited about agile programming. And there was this book called Extreme Programming. And I thought, this is what we need in the climate system model that I work on. And I did a little talk on it, and instantly, my hopes about that were crushed. And so this is kind of a long-term story since then about bringing agile methods in. So, here's the problem, and various people have been talking about this, is that we have scientists that contribute to our code, the community terrestrial system model, and they contribute a ton of code, and of course it's all about science, and so that's what's important. And then we have on the other side, we have the software engineers that also contribute code, and sometimes they don't necessarily talk together, and sometimes, I mean, the scientists aren't necessarily, well, they're not trained in RSE practices, right? They need to concentrate on their science, but we really need to encourage better software development practices from everyone. So increasing the collaboration between the research software engineers and the code contributors really helps. So now part of this talk is a presentation that I made to our scientists, and we'll kind of talk about that a little bit. But this is really the story of adding lines of communication and collaboration, because I think if we collaborate more closely together and we're working together, we can end up with better code. So. What is CTSM and why should scientists care about it? And there's all the science down in the box there. But CTSM fundamentally is science expressed in software. And that means if you touch any of the CTSM code, you're an RSE, you're a research software engineer. So anybody that touches science code is a research software engineer, and let's just embrace that fact. Okay, so, but also another important thing is that bad software practices kill our science. Clean software and software development practices make CTSM science easier and flexible, more flexible and robust and verifiable and correct and reproducible. So that's really important to come in. So how do we encourage scientists to improve our coding practices? So these are some ideas that I have. First, help them to see that poor code impacts the science. Let's see, there we go. When problems come up, examine the causes and how to prevent them. Point out the missing practices that could have helped. Pointing out the cost of having poor practices and how that's greater than the cost of having good practices. Okay.
And then here's an example of that. So one of my teammates, Adriana Foster, added a little bit of code that it's a functional testing around a science routine. And she noticed, she ran it over different inputs and found the thing in red is obviously something that's odd. And so she was able to, identify a bug in the science by looking at doing finer scale testing. So part two, how do we encourage scientists to improve coding practices? One thing is to make sure their RSE work is recognized as critical to model development. A lot of us have been talking about that, and this is kind of something leadership has to do. So one thing is recognition in scientific papers and team awards and that sort of thing, and NCAR has been good about that for me. I'm added to papers that I don't contribute to other than working on the software, which I appreciate. And leadership recognizes the importance of RSE work. And RSEs are celebrated and treated well and not less than scientists. That's something that, in my opinion, when I first came to NSF NCAR, I was kind of treated like I was less than the scientist, but now I feel like I'm more on an equal footing, which is a much better environment to work in and to do good work in. So part three, how do we encourage scientists to improve coding practices? And I realized that they are not trained in RSE practices. It's not something they don't need training in. And so we, as RSEs, need to educate them on what's most important and that they can accomplish. So part of that is that the RSEs have to actively be doing and be expert in those practices so we can teach them to people. And we need to have education resources available, tutorials, documentation, et cetera, about how to do these things. So one of the practices that we went to from SVN to Git, several years ago, and we came up with some documentation, a tutorial, and we had a program about that, and that really helps people. So because Git is so fundamental to everything right now. Another thing I realized is that probably a better way to talk to scientists is to use metaphors and non-technical terms. So instead of technical terms that are used in the software industry, because, again, they're not trained in these things. So that's part of what I'll show here. And encourage people that try and provide help to them. So anybody that tries, that's great. So so some red things that I'm realizing that need to happen that we haven't really done is that you need to continually do education on the practices. There continually needs to be education on Git and that sort of thing. Probably you need to introduce one practice at a time. I'm going to show you some slides that I showed to the Land Model Working Group. And I realized I literally told them about 10 practices and didn't follow this. So I'm thinking about how we need to do that. And make the most important things easy. I highlight Adriana again. She was adding some functional testing. And one of the things that she did was to make it easy to add a functional test. Which is an awesome thing to do because then it makes it it makes it possible for a scientist to go in and replicate what she did for some other part of the science. So realize that's important. Things that do not work. Lots of things there. Okay, so there's tons of stuff here. I'm not going to go through them all. Whoops, let me go back. Okay. So a lot of this is about not being a good collaborator and being condescending or something like that, or expecting too much of somebody that's not their job. Scientists, it's not their job to be an RSE. So now Ed Hartnett, I love his approach. As a manager, he can just say, you got to do it. Since I'm not a manager, I've just found we have to be more subtle in how we approach things. But make sure if people understand the impact and the benefits, then they'll actually do it. So what does work? So what I'm thinking, oops, there we go. So demonstrate the costs for bad practices and demonstrate those practices so others can adopt them, educate on the practices, and then work with the people with the highest interest in RSE work. So in our team, Adriana Foster and Sam Raven both have a high interest in both the science and the software practices, which is really awesome to have. That's not what you necessarily always have. So, but people that have an interest in research software engineering, let's utilize them and help them out in the best way we can. So, okay. So, what makes doing RSE task hard? And Ed Hartnett talked about this with the legacy programming. And the question here is, what can we learn from the software engineering industry for research software engineering? And the big thing is that debugging is the most expensive thing we do. So I put a $100 bill there because it is very, very expensive in multiple ways. Inherently intractable, we can't make estimates on when you're going to fix a bug. The further along in the development, the more expensive it is. If you have a bad design from the get-go, you build in the right requirements, it's going to be really hard to debug down the line. So, and this is what we find out from the software engineering industry. And in practice, brittle, poorly designed, poorly tested code keeps you constantly debugging. So it keeps you in this expensive part of the work. So, in our team, we kind of did a little estimates on this. So a practice that we've been doing with me and one other person in my team is we've been doing estimations, and then we do a 4-week sprint cycle, and we do some planning before and some post view afterwards, that kind of thing. And so the tasks that I did a lousy estimate on, most of them were because of some debugging issue. And so, it looked like I was spending about half my time on debugging, and I like to call it debugging hell. Debugging hell, not a good place to be. And, I just asked my team the last few weeks about what it looks like for them. And, they're thinking about, 20% of the time. And so that's expensive. And the other thing that we realized is that we need to identify when we're in debugging hell, let's identify problems with the code so that we can fix them. So that we can, and the idea is you refactor to improve the code for stuff that's commonly changed and is problematic enough. So what practices does the software industry show helps? There's 3 practices: requirements, design, and testing. RSE maximum to live by. When I first heard this, I realized that was my life. Untested code is broken or will get broken if you continue to change it and you don't test it. So don't do these things, and do these things about test suites. And I asked my the scientists in an informal survey, what do you do when you find the code is broken? And the question is, what can we learn from that? And most people ask someone else, which probably means we have a good community to help. But that's really time consuming for the RSE staff. And this kind of communication doesn't really result in a fix coming in. About a quarter ask on the forums or create an issue, which is better for tracking. So we probably want to increase that fraction. A small number could fix the problem, so there's at least knowledge for some people, but also shows in general the model is complex enough that this is hard to do. Improving our testing should help all users to have less problems that need to be fixed. And no one selected give up and move on, which is good news. So here's my list of RSE suggestions. And I'll just list them pretty well. So there's small circle jujitsu, which is going towards agile as opposed to waterfall. Trim the fat, which is requirements, draw the building, which is design, preserve success, which is version control, practice vulnerability, which is openly share your code and issues, and then trust but verify, so test-driven development, and then improve the design as you go, which is refactoring. So, and I'll go through this quickly. So we've talked about waterfall versus agile, and we really do both of these things in our development, but we're realizing that I think it's probably better if we do more towards the agile is what we want to try to work towards. So trim the fat is about requirements, and Daniel, right, talked about the statement of work. I think this is a lot of what this is that if you do some planning and you figure out what you need to build and when you're going to be done, that just really helps. Draw the building, which is design, code changes before starting. Phil talked about this a little bit on a different perspective because in our development, I think we've been too low on doing design before we code. But I know other places you do a whole design doc and you have, but it's so big that nobody wants to look at it. And so we're talking about, the main thing that's important here is that you think about design before you go on. So think about design, maybe have a short document about it. Preserve success is Git. Practice vulnerability. Everybody's embarrassed about their code. So we have the embarrassed polar bear. Everybody's that way. But it's really important to have if you want to improve it and not be embarrassed, you have others review your code. It's the best way to improve. And really the code is a shared resource that the whole team is responsible for. Same with bugs. And so if we work together as a team, that's going to be far better. Trust but verify, test-driven development. And I just want to highlight Adriana again because of her functional testing for science. Improve design as you go, refactoring. But the only way you can do refactoring is if you have sufficient testing in place so that you can improve the design as you go, right? So questions. And actually, I have questions for you. How do we encourage scientists working in code to improve their development practices? How do you survey code contributors on their practices? And how do you measure success? Oops. Okay, thank you.
Thanks, Eric, and congratulations on your persistence.
Okay, okay, thank you.
Any questions for Eric? Or responses to his questions?
Answer these, yeah.
Yeah, I'm going to start with a question.
Cool.
You said start small, so you just listed I think 7 things I counted that we could do.
Yeah.
What are your top 2 that we should start with our scientists?
I think it might depend on which one and where you're at with them. And so like one of the first things we established with scientists is that you got to work in Git. And so, but a lot of people are now involved in Git, and but if you can train somebody new, that's like the first thing you got to work with. So, but I did say the top 3 are requirements design and testing. And so if you're talking about an individual, I think which of those would help them the most, I think is the thing to start with. And yeah, it's a question in my mind that I realized, we have I came up with these 10 things or whatever it is, and we have to figure out which one we're going to focus on to make sure it's established for the team so that we can then go to another one. But yeah, but it's a great question.
I have a question and a response.
Awesome.
I'll start out with my response really quickly to how do you encourage scientists working on code to improve their development practices? I think for me, I've found that sharing success stories is helpful. So talking about other scientists that we've worked with in the past who were for example, taking Git, for example, very uncomfortable with Git, but then became comfortable with Git and sharing just how much it improved their lives. So I think that's one thing. And then also connecting to the point that you made about vulnerability, I also share with the scientists that I'm working with how uncomfortable I was with Git when I first started.
Oh, yeah.
And obviously I'm on the software engineering side, but I also started from nothing at some point in time. So I think sharing that vulnerability with them, I think has also helped me. But I
That's
just wanted
nice.
to say,
Awesome.
great talk. And I really appreciate amazing, like many, many amazing points. I think particularly the actionable items that I really liked was like focusing on one practice at a time.
Yeah.
But my question is,
Okay.
in your experience, do you have particular advice for how to help people get over the discomfort that they might face? Because I think discomfort's part of the educational process. So do you have any sort of?
Oh, that is a really good question. I mean, I think that's the vulnerability though that really helps with that is because if I can say, Git is really complicated. It took me a long time to even get the conceptual model. I think that can help. So, because we were having to talk about psychological safety, and that if people are able to say this was difficult for me, then it's easier for them to feel better about um, having it be difficult for them, and for them to expect, this is going to be hard. But in those, we can help you and that sort of thing. Because if it's hard and nobody's going to help you, then it's even harder. So I don't know if I have an answer to the question, but I think having good team dynamics really helps. That is one thing.
Oh, I agree. Thank you so much.
Yeah.
You mentioned you have a Git documentation and tutorial that you shared with scientists. Can you share that with all of us?
Oh, okay. I didn't even think of that. It's really tailored.
Starting point.
It's really tailored to how we use it in CTSM, and actually we did that a few years ago, and so I'm not even sure how relevant it is now. But
So it's not really general Git
yeah, it's not
stuff.
very general, but because there's lots of resources that are general Git, and so this was like, but I think this is useful to do though, is to how do you use Git in your particular environment. Which is just really important because people can see so much stuff that they can just get easily confused by. What do I need to know for CTSM? What do I need to know for the project you work on? I think that's really
Yeah, and I'm
helpful
a
to
scientist.
customize.
How do I even start figuring out Git? I don't want to tell my scientist, go online and find a tutorial, right?
Right, exactly. But have one customized for your project. Yeah, exactly. Good. Cool.
Yeah, thanks for the talk, Eric. I think just tying together maybe the two prior comments, I feel like one thing I've liked is kind of thinking about tailored tutorials. I like seeing somebody make some mistakes in their tutorial, which obviously entails live demoing. But I think back to when I was first trying to learn Pandas, I found some tutorials on YouTube by, I think it was Brandon Rhodes. And first off, I mean, he was hilarious. Like, I didn't think I would laugh so much at a Python tutorial, but it was great. But the entire 2-hour tutorial was just him, live at a terminal and complaining about when Python would annoy him and stuff like that. And it was very human. Like, it was a very real experience that you would have sitting down at a terminal. So I feel like when you give a tutorial and it just shows the end result, it can be daunting. But if you start from the beginning of the learning process and then bring people through, then maybe they feel like, oh, okay, it was the same way for them that it's turning out to be for me.
Right. That's cool. I love that. Yeah. Yeah. Thanks. Okay. Cool. Thank you.
Yeah, great discussion, and thanks, Eric. And just a reminder, we're going to be around for the next hour from let's see here, it's 2:02 now to 3 o'clock today to answer any of the questions and help you with your notebook proceedings. So please stop by. And just a reminder that those are due at the end of the week, which is unfortunately tomorrow. So we highly encourage you guys to share your presentations. It's been a great workshop. I definitely have learned a lot, and I've enjoyed meeting new people, and it's been a great experience. So I want to thank all of you guys too for a great conference. And that's it.
Yeah, I mean, like, we still. Okay, thank you. It's in progress. It's beginning to be. If he wants it. As these. So there's a areas. Yeah, you're forward effort to make that stuff all kind of proud and great. Yeah, I mean, there might be like some opportunity.
Are you, oh, so there's like a, so.
Okay.
Yeah, so it's like.
I think it'd be good. I mean, I know that we. Yeah.
A lot of the folks are involved, I guess, like.